picture a perfect void, not just an empty room or the dark between the stars. I mean a place with absolutely nothing in it. No matter, no light, no energy. Not even space or time. Just pure, absolute nothing. It's an idea that feels both simple and a little terrifying, doesn't it? But what if I told you that this perfect nothingness is a ghost? It's a concept our universe simply forbids. The very laws of physics and the structure of reality itself make true nothingness impossible. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. For centuries, thinkers have been obsessed with a huge question. Why is there something rather than nothing? It feels like nothing should be the default setting, the simplest and most stable way for things to be. And yet, here we are, in a universe overflowing with galaxies, stars, planets, and, well, us. To even get a handle on this, we have to ask what nothing really means. The idea seems simple, like a blank canvas. But as we peel back the layers, moving from our everyday ideas to the bizarre world of quantum mechanics, that simple idea of nothingness starts to fall apart. It twists itself into a paradox, something that's logically and physically impossible. We're going to take that concept of emptiness and see what it's really made of. We'll start with the nothing we think we know, then look at the empty spaces we actually find in the world. From there, we'll see how the fundamental laws of physics aggressively prevent a true void from ever existing. We'll discover that even a perfect vacuum is actually a raging sea of activity, and that space and time themselves are something that can't just be turned off. And we'll even see how ancient philosophy, from both the East and the West, wrestled with this idea and, in many ways, arrived at the same conclusions as modern physics. By the end, you'll not only see why absolute emptiness is a contradiction, but you'll also see how its impossibility reveals a deeper truth about the vibrant and interconnected nature of reality itself. The nothing we think we know, intuitive emptiness. Let's start with that gut feeling. When you hear the word nothing, what do you picture? For most of us, it's a concept built on absence. Think of an empty room before you move in. It's a defined space, a container, but it's waiting for the things that give it character: no chairs, no tables, no art. It's pure potential. Or imagine a pitch-black closet before you find the light switch. For that split second, there's no color, no shape, just a sensory void. This is our intuitive grasp of nothing. A total blank slate. This version of nothingness can feel weirdly comforting. It's a reset button, a ground zero from which everything else can grow. It's the silence before the music starts, the clean page before the first word. In our minds, this intuitive nothing is just a passive backdrop. It doesn't do anything, it's just the stage where somethings can show up. It's the ultimate state of simplicity, a peaceful quiet that makes the chaos of existence seem like an optional extra. This idea is baked into our psychology and our language. We talk about starting from nothing, or having nothing to lose. In these phrases, nothing is a baseline, a starting point. It's a conceptual floor. We assume that something and nothing are opposites. A box is either empty or it's not. A space is either occupied or vacant. But this simplicity is exactly what makes it so misleading. Our intuition is built for a world of objects and containers. So, naturally, we think of absolute nothingness as the ultimate container, one that just happens to be empty. But what if the container itself is part of the something? What if there is no box? What if the very ideas of inside and outside break down when you push them to the absolute limit? This intuitive idea of nothing as a quiet, empty stage is the first domino we need to knock over. the emptiness we actually experience, relative voids. Okay, let's bring the idea of emptiness down to earth. What about the empty spaces we see every day? Are they really nothing? Take an empty coffee cup. We call it empty because it's empty of coffee. But is it a void? Of course not. It's filled with air, a chaotic mix of nitrogen, oxygen, and other gases bouncing around at hundreds of miles per hour. Not to mention dust, bacteria, and all sorts of microscopic stuff. It's not empty at all. It's just empty of what we expected it to hold. This is a asterisk relative empty. Let's go bigger. Think about the emptiness of outer space. We call space a vacuum, and compared to our atmosphere, it sure is. But it's far from true nothingness. Even in the massive voids between galaxies, the intergalactic medium still has, on average, about 1 hydrogen atom per cubic meter. That space is also shot through with a constant shower of photons and neutrinos, not to mention invisible gravitational and electromagnetic fields. And that's before we even get to dark matter and dark energy, which are believed to make up most of the universe. The vacuum of space is actually a very thin soup of particles, radiation, and energy. Even the best vacuums we can create on Earth don't come close to absolute nothing. In labs like CERN, scientists use powerful pumps to create ultra-high vacuum chambers, getting down to just a few hundred particles per cc. But they can never, ever hit zero. For one, the walls of the chamber itself constantly shed atoms in a process called outgassing. If you somehow made a vacuum powerful enough to approach a perfect void, it would literally start tearing particles out of the chamber walls to fill itself. The ancient philosopher Aristotle had a phrase for this: horror vacui, the idea that nature abhors a vacuum. He was onto something. Every example of emptiness we can find is never absolute. It's always a state of less matter, less pressure, less energy. These are all relative voids, defined by the absence of things we notice, but they're never truly barren. This suggests that maybe the universe doesn't work in a binary of all or nothing. Maybe it's just a continuum of something, from incredibly dense to incredibly thin, but never reaching zero. So the real question is, why? Why can't we get rid of that last particle, that last flicker of energy? To answer that, we have to enter the strange world of quantum physics. The physics of the void. Why the universe forbids nothingness. This is where the idea of a simple, peaceful void completely falls apart against the laws of reality. Modern physics doesn't just say absolute emptiness is unlikely, it shows it's fundamentally impossible. At its most basic level, the universe is a place of endless activity. There is no off switch. Let's start small. In quantum field theory, the basic building blocks of reality aren't little particles. They're huge, invisible fields that fill all of space and time. There's an electron field, a photon field, and so on for every particle. What we think of as a particle is just a little vibration in its field. So you might think, okay, just get rid of all the vibrations, and you have nothing. But you don't. You're left with the fields themselves in their lowest energy state, the vacuum state. And that is far from empty. This is because of one of the weirdest rules in quantum mechanics: the Heisenberg Uncertainty Principle. One version of it says there's a fundamental trade-off between knowing a system's energy and the time it has that energy. You can't know both perfectly. Because of this, the energy in any patch of space can't be perfectly and constantly zero. If it were, you'd know its energy, zero, and its momentum, also zero, with absolute certainty, which violates the principle. So, what happens instead? The vacuum hums with energy. This rock-bottom minimum energy is called *0 energy. And it isn't quiet. It constantly fluctuates, creating a bubbling, roiling frenzy known as *quantum foam or *vacuum fluctuations. Out of this seething energy, Pairs of virtual particles and their antimatter twins spontaneously pop into existence, exist for an impossibly short time, and then destroy each other, returning the energy they borrowed. An electron and a positron, a quark and an antiquark, they flicker in and out of existence everywhere, all the time, in even the emptiest space. We can't see them directly, but their effects are real and have been measured. The Casimir effect, for example, is a real, measurable force that pushes two metal plates together in a vacuum. The most accepted explanation for this is that more virtual particles are popping into existence outside the plates than between them, creating a tiny amount of pressure. So, empty space isn't empty. It's one of the most dynamic places imaginable. Absolute nothingness, a state of zero energy and zero activity, is forbidden. The universe simply can't hold that still. Now let's scale up to cosmology with Einstein's theory of general relativity. Before Einstein, we thought of space as a static, empty stage. But Einstein showed that space and time are woven together into a single, dynamic fabric, spacetime. And this spacetime isn't just a backdrop, it's a physical thing. It can be bent, stretched, and rippled. What we call gravity is just the curvature of spacetime caused by mass and energy. The fact that spacetime can act on matter, by telling it how to move, and be acted upon by matter, by getting curved, means that spacetime is a something. This creates a huge problem for the idea of absolute nothingness. If nothingness is the absence of everything, it must also be the absence of spacetime itself. But what does that even mean? Where would this nothing be? The word where requires space. How long would it last? The word last requires time. Without the framework of spacetime, you can't even describe a void. To have absolute nothing, you'd have to get rid of the entire universe, including the very stage it's built on. Within our current understanding of physics, you just can't do that. So physics traps the concept of nothingness from both sides. Quantum mechanics says that even if you had an empty stage, it would instantly start boiling with activity. General relativity says the stage itself is a physical thing that you can't get rid of. The baseline of our reality isn't zero. It's a humming, fluctuating, dynamic something. The central contradiction, the philosophical paradox of nothing. We've seen that physics bans absolute emptiness. But the problem goes even deeper. The very idea of absolute nothingness is a logical paradox, a concept that contradicts itself the moment you try to describe it. It's a snake eating its own tail. Let's try to pin it down. Absolute nothing means the total absence of everything. No particles, no energy, no space, no time, no physical laws, no properties at all. It's not an empty space, it's the lack of space. But here's the trap. The moment you say that absolute nothingness is, or exists, you've given it a property, the property of existing. But by definition, nothingness can't have any properties. If it exists, it's no longer nothing. It's a contradiction. To even talk about it is to treat it like a something. Let's try another angle. Let's say you could create a bubble of perfect nothingness. What defines its border? The edge between the something outside and the nothing inside would itself be a feature, a piece of information, a something. For nothing to be absolute, it can't have a boundary. It can't be contained. This leads to an even stranger problem, the so-called instability of nothing. Let's pretend for a second that a state of absolute nothingness was possible. This state would have no properties, meaning no rules, no laws, and no limitations. A law like, you can't create matter from thin air, is a rule that governs a system. But in pure nothingness, there are no rules. There's nothing to forbid anything from happening. and if there are no rules to forbid possibilities, then every possibility is on the table, including the possibility of something. The state of absolute nothingness, because it has no rules, inherently allows for the state of something to arise. It's a fundamentally unstable condition. In this view, the first cause of the universe wasn't some external event, but the simple logical impossibility of non-being. Ancient Greek philosophers like Aristotle wrestled with this. He argued that a void was incoherent, famously declaring, "Nature abhors a vacuum." For him, this wasn't just about physics. It was a metaphysical claim that being is fundamental, and non-being is just a fiction of logic. This philosophical paradox mirrors what physics tells us. Physics shows a vacuum is unstable and bubbles with virtual particles. Philosophy shows the asterisk concept of nothingness is unstable and bubbles with contradictions. You can't describe it without turning it into something. The hole in the donut is only defined by the donut around it. True nothingness would have no donut, nothing to define it against. And in that state, it stops being a concept we can even grasp. Eastern philosophical perspectives. The fullness of the void. While Western thought has often treated nothingness as a problem, many Eastern traditions have approached it from a completely different angle. In philosophies like Buddhism and Taoism, emptiness isn't a terrifying void but a profound concept pointing to the true nature of reality. Their idea of emptiness, however, is radically different from the absolute nothing we've been trying to imagine. In Mahayana Buddhism, the key concept is sunyata, usually translated as emptiness. Now, it's easy to hear emptiness and think it means nothing exists, or life is meaningless, but that's missing the point entirely. Sunyata doesn't mean things don't exist, it describes how they exist. It's the teaching that all things are empty, of a fixed, independent, standalone self. Think of it this way. What is a tree? A tree isn't one solid thing. It's a temporary convergence of sunlight, water, soil, and air. It exists in a web of relationships with everything around it. Take away the sun, the tree dies. Take away the soil, it can't grow. Its treeness isn't some core essence inside it. It's a dynamic process of interdependence. This is what it means for the tree to be empty. It's full of everything else. This applies to us, too. Our sense of a permanent, separate self is an illusion. You are a constantly changing flow of thoughts, feelings, and sensations, all dependent on causes and conditions. Realizing this emptiness, this interdependence, is the key to freedom from suffering. So, for Buddhism, emptiness isn't a void, it's a dynamic, relational fullness. It's seeing that reality isn't a pile of separate rocks, but a flowing river where everything is connected. Taoism offers a similar view with the concept of wuji, often translated as limitless or primordial. Wuji is the unmanifest state that comes before all creation, often shown as an empty circle. It's a void that is paradoxically full of infinite potential. From this silent, formless ground of being, the duality of yin and yang and then everything else in the world emerges. This isn't a destructive nothingness. It's the silent, generative source of everything. In both traditions, the sterile nothingness of Western imagination is replaced by a dynamic, fertile, and interconnected emptiness. This perspective doesn't contradict modern physics. It enriches it, offering a language of wisdom to complement the language of math. Western philosophical perspectives. The nothingness of consciousness. While Eastern thought sees emptiness as interconnectedness, Western existentialism, especially in the work of Jean-Paul Sartre, took the idea in a much more personal and unsettling direction. For Sartre, nothingness isn't out there in the cosmos. It's something that we, as humans, bring into the world through our own consciousness. In his huge work Being and Nothingness, Sartre splits reality into two modes. The first is being in itself. This is the being of objects. A rock, a table, a planet. These things just are. They are solid, complete, and totally determined by physical laws. The second mode is being for itself and this is us. This is human consciousness. Unlike a rock, consciousness isn't a thing. It's always conscious of something. It's defined by what it is not. Sartre makes the radical claim that consciousness, in its purest form, is a nothingness. He means that at the core of our being is a fundamental lack, a void. And it's this nothingness that makes us free. Because we aren't a fixed something. Like a rock, we can say no to our current situation, imagine different possibilities, and choose our own future. As he famously put it, existence precedes essence. We are born without a defined purpose, and we have to create who we are through our choices. We are, in his words, condemned to be free. This freedom, born from nothingness, is also the source of our greatest anxiety. We are responsible for our lives, with no excuses and no script to follow. This can lead to bad faith, when we flee from our freedom by pretending we are a fixed object. The waiter who acts like a perfect automaton, completely identifying with his role, is in bad faith. He is denying his freedom to be anything else. So for Sartre, nothingness isn't a physical void, but an existential one inside us. It's the gap where our freedom lives. It's the unsettling discovery that there is no solid core to our identity. And while that's a frightening thought, it's also what allows us to create meaning in a universe that doesn't hand it to us. This journey into nothing touches on the deepest questions we can ask. Each perspective, from the quantum foam to Buddhist emptiness to Sartrean freedom, reveals a completely different face of this impossible concept. Which one resonates with you the most? Is nothingness a physical impossibility, a philosophical word game, or a personal experience? Let me know in the comments. And if you enjoy wrestling with ideas that stretch the fabric of reality, be sure to subscribe so you don't miss our next journey into the unknown. We started with a simple idea, a perfect, empty void. And we've watched that idea get dismantled by every tool we have to understand reality. Physics tells us the universe refuses to be empty. The uncertainty principle guarantees that even a perfect vacuum seethes with energy and virtual particles. General relativity shows us that spacetime itself is a physical something that can't be deleted without taking the whole universe with it. Philosophy shows us that absolute nothingness is a logical trap. The moment we try to define it, it becomes a something. Ancient wisdom reframes emptiness not as absence, but as limitless potential and total interconnection. And existentialism finds a kind of nothingness right inside us, the void of essence that gives us our freedom. So, why can't absolute emptiness truly exist? Because the universe isn't a static box with things in it. It's a single, dynamic, interconnected whole. The quantum fields are the universe. The space-time fabric is the universe. The web of causes and conditions connecting every star to every one of us is the universe. You can't remove parts one by one until nothing is left, because no part is truly separate. The impossibility of a true void is, in the end, a deeply optimistic truth. It means that, on a fundamental level, there is no true isolation. There is no true finality. Reality isn't a fragile thing hovering over an abyss of nothing. Reality is a restless, unbreakable, and endlessly creative dance of being. The next time you feel a sense of emptiness in a quiet room, a lonely moment, a feeling of loss, remember what the universe shows us. It's never truly empty. It's just a space humming with hidden fullness, waiting for the next possibility to emerge. The universe doesn't do nothing. And in that simple fact lies all the wonder of its existence. The biggest lie in physics is empty space. What do you see when you look up at the night sky? Stars, planets, maybe a galaxy if you're lucky. But mostly, you see the gaps in between. A vast, silent, empty void. This is what we're taught space is. It's our deepest intuition about the universe that it's mostly made of nothing. But this image is a lie. The biggest, most persistent, and maybe most consequential lie in all of physics is the idea of empty space. The truth is that the most perfect vacuum we can imagine, a region of space scrubbed clean of every single particle, isn't a tranquil void. It is a raging, chaotic sea of invisible energy and phantom particles, constantly erupting into existence and vanishing in an instant. It's a concept so bizarre it sounds like science fiction. But it's not. It is a fundamental feature of reality. And the most incredible part? Scientists have proven it. Today, we journey into the heart of nothingness itself, to uncover the profound and mind-bending truth hidden inside. We're going to see how this lie of empty space falls apart, piece by piece, from the strange rules inside the atom all the way to the ultimate fate of the cosmos. By the end of this, you will never look at the empty space in a room, or the darkness between the stars, in the same way again. The universe isn't what it seems. And the story starts a long, long time ago, with a simple, ancient question. What is nothing? The classical void. A history of nothing. For thousands of years, the concept of nothing has been a battleground for philosophers and scientists. The ancient Greeks were the first to really formalize the debate. On one side, you had thinkers like Democritus, who imagined the world was made of tiny, indivisible particles he called atoms, zipping through a limitless void. For Democritus, nothing, the void, was just as real and necessary as something, the atoms. Without the emptiness for them to move in, the universe would be a frozen, unchanging block. But this idea was deeply unsettling to others. Aristotle, whose influence would dominate Western thought for almost 2 millennia, rejected it completely. He famously declared that nature abhors a vacuum. For him, the idea of a true void was a logical paradox. How could nothing exist? If it exists, it must be something. He argued that space was a asterisk plenum, a substance that was filled everywhere, with no gaps. You could suck the air out of a container, but something else, some ethereal substance, had to rush in to fill its place. This Aristotelian view held on for centuries. Even as the scientific revolution dawned, the idea of a truly empty void was hard for people to accept. René Descartes, a foundational figure in modern science, sided with Aristotle, arguing that the very definition of space was extension, and where there's extension, there must be substance. A vacuum just wasn't possible. It was Isaac Newton who gave the void its modern, classical form. His laws of motion and universal gravitation described a universe where objects moved through an absolute, unchanging, and totally passive stage, empty space. This space didn't do anything. It was just there, a featureless container for all the matter and energy. Yet, even this clean, simple picture didn't last. In the 19th century, as scientists wrestled with the nature of light, they brought back the idea of a plenum. How could light, an electromagnetic wave, travel through the complete emptiness of space? As far as they knew, waves needed a medium like sound through air or ripples on a pond. So, they invented the luminiferous ether, an invisible, undetectable substance that filled all of space, giving light something to travel through. The ether was the ultimate cosmic fudging factor, a placeholder for something they knew had to be there, even if they couldn't see it. Of course, the famous Michelson-Morley experiment in 1887 failed to detect this ether, delivering a fatal blow to the idea. This paved the way for Einstein's theory of special relativity, which didn't need an ether at all. With that, physics seemed to have finally settled the question. The ether was gone. Space was empty. The classical void, a vast expanse of pure nothingness, was back. And for a brief moment in history, that was the end of the story. The lie was complete. But at the exact same time, a revolution was brewing. A new kind of physics was emerging, one that would look deep inside the atom and at the very fabric of space itself, and find that it was anything but empty. The atom's emptiness. A familiar illusion. The journey to dismantling the lie of empty space starts with something we all learned in school. The atom. We were taught that an atom is made of a tiny, dense nucleus, with even tinier electrons whizzing around it. And the most astonishing fact was always the scale. If the nucleus were the size of a marble in the center of a football stadium, the electrons would be like specks of dust out in the bleachers. The rest? It's empty space. Over 99.9% of an atom is nothing. This single fact should shatter our intuition about the world. If the atoms that make up a solid wall are mostly empty space, why can't you walk through it? If you, and the wall, and everything we think of as solid, are just loose collections of tiny particles separated by huge voids, what gives matter its substance? Why doesn't the world just collapse into an ultra-dense soup? The answer is our first clue that empty doesn't mean powerless. The solidity you feel isn't from tiny billiard balls bumping into each other. It's the result of invisible forces and strict, unbreakable quantum rules that operate in the empty space inside the atom. The first piece of the puzzle is the electron itself. We used to picture electrons orbiting the nucleus like planets around the sun. But the modern quantum view is far stranger. An electron isn't a tiny dot at one specific location. It's a probability cloud, a smear of potential where the electron could be. This cloud is the electron's quantum state, and it effectively takes up the entire volume of its orbital. When you push your hand against a wall, you're not actually hitting a solid surface. You're bringing the electron clouds of your hand's atoms close to the electron clouds of the wall's atoms. Since both are negatively charged, they repel each other ferociously through the electromagnetic force, just like trying to push the same poles of two magnets together. This repulsion is what creates the sensation of touch and the feeling of solidity. You aren't touching the wall. You're being pushed away by an invisible force field. But there's an even deeper, stranger rule at play, a principle that is arguably the true source of all structure in the universe. The Pauli exclusion principle. Discovered by the brilliant and notoriously critical physicist Wolfgang Pauli, this principle is deceptively simple. No two identical fermions, the category of particles that includes electrons, protons, and neutrons, can occupy the same quantum state at the same time. Think of quantum states like seats in a movie theater. When you fill an atom with electrons, the first two can take the best seats in the house, the lowest energy orbital, one with spin up, and the other spin down. But once those two seats are taken, the next electron is excluded. It's forbidden from squeezing into that lowest level. It has to occupy the next available energy level, a higher and larger orbital. This continues, with each new electron forced to stack into progressively higher energy states, creating the famous shells of an atom that are the basis for the entire periodic table and all of chemistry. This principle is what prevents matter from collapsing. The reason you don't fall through the floor isn't just because of electromagnetic repulsion. It's because the electrons in the floor and the electrons in your shoes are all fermions, and they refuse to be in the same place with the same state. If you try to force them together, they resist with a powerful outward pressure called degeneracy pressure. This pressure has nothing to do with charge. It's a fundamental rule of their quantum identity. It is the universe's way of saying, sorry, this level's full. Without the Pauli exclusion principle, all the electrons in every atom would collapse into the lowest energy state, and the rich, complex world we know just wouldn't exist. So, the emptiness inside an atom isn't a passive void. It's a domain governed by powerful forces and ironclad quantum laws. It's filled with probability clouds and exclusion zones. It is structured, and that structure is what gives our world substance. This is the first crack in the lie of empty space. But to blow it wide open, we have to zoom out from the atom and ask an even bigger question. What is the space between the atoms made of? The turning point. The rise of quantum fields. For centuries, our model of the universe was one of particles and the void. But this, it turns out, is the wrong way to think about reality. The true foundation of the universe isn't particles. It's fields. The idea of a field was first introduced back in the 19th century by Michael Faraday to explain the mysterious nature of electricity and magnetism. He imagined invisible lines of force stretching through space, and this concept, a physical quantity that has a value for each point in space and time, was revolutionary. Quantum field theory, or QFT, is the modern culmination of this idea. It's the marriage of quantum mechanics, special relativity, and classical field theory, and it is the most successful physical theory ever devised. QFT tells us that the most fundamental building blocks of the universe aren't particles, but the fields themselves. There is an electron field that permeates every single point in the universe. There's a photon field, a quark field, a Higgs field, one for every fundamental particle we know. In this picture, what we call a particle, like an electron, is nothing more than a localized excitation, a ripple, a vibration, a concentrated knot of energy in its corresponding field. Think of the entire universe as a vast, calm ocean made of these interpenetrating fields. If you tap the electron field at one point, you create a ripple. That ripple is what we measure as an electron. When particles interact, it's just ripples in one field causing ripples in another. This is a profound shift in perspective. Particles aren't fundamental. They are temporary manifestations of the more fundamental, ever-present fields. The fields are the true reality. The particles are just the tune being played on them. So here's the crucial question. What happens to these fields in a perfect vacuum? What are they like when you remove all the particles, all the ripples? In classical physics, the answer would be simple. They'd be zero. A field with no excitations would be flat, dormant, and have zero energy. But quantum mechanics has a very different answer, found in one of its most central tenets: the Heisenberg Uncertainty Principle. Introduced by Werner Heisenberg in 1927, the uncertainty principle states that there are pairs of properties you can't know with perfect accuracy at the same time. The most famous pair is position and momentum. But another version of this principle relates energy and time. It says you can't know the exact energy of a system if you only measure it for a very short amount of time. There's always a fundamental fuzziness. For very, very short moments, the energy of any system can fluctuate wildly. Now, let's apply this to the quantum fields in a vacuum. A field that is perfectly flat and still, with an exact energy of precisely zero, would violate the uncertainty principle. If its energy were exactly zero, its value would be perfectly known, and that's forbidden for a dynamic quantum system. So, what happens instead? The fields can never be perfectly still. They must constantly roil and jitter, even in their lowest possible energy state, the vacuum state. This residual, irreducible energy that fills all of space, even in a total vacuum, is called *0 energy. It is the energy of nothingness itself. And this leads to the most bizarre consequence of all. Thanks to these energy fluctuations, the fields can momentarily borrow energy from the vacuum. If there's enough borrowed energy, it can create a particle-antiparticle pair, seemingly out of thin air. These particles exist for an impossibly short time before they collide and annihilate each other, paying back their energy debt. They flicker in and out of existence, a phantom froth on the surface of reality. They are called virtual particles. This is the ultimate dismantling of the lie. The vacuum is not empty. According to quantum field theory, it's a plenum, just as Aristotle imagined, but a much stranger one. It's filled with potential, with jittering fields and a constant flux of virtual particles popping in and out of existence everywhere, at every moment. This sounds like theoretical fantasy. A boiling sea of phantom particles we can never see. How could we possibly know this is real? For decades, that was a fair question. But then, an experiment was proposed that would drag these phantom particles from abstract math into the real, physical world. The smoking gun. The Casimir effect. In 1948, the Dutch physicist Hendrik Casimir was at Philip's research labs, studying the sticky forces between molecules. During a chat with the legendary Niels Bohr, Bohr mused that these forces might have something to do with the vacuum's zero-point energy. Intrigued, Casimir came up with a startling prediction. He imagined a simple setup. Take two perfectly flat, uncharged metal plates and place them parallel to each other in a perfect vacuum, just micrometers apart. Classically, nothing should happen. No charge, so no electromagnetic force. No air, so no pressure. The plates should just sit there. But Casimir realized that if the quantum vacuum was a sea of virtual particles, the story changes. He predicted a force would arise from the vacuum itself, pushing the plates together. This is now known as the Casimir effect. The explanation is as elegant as it is mind-bending. The vacuum is filled with virtual photons of all possible wavelengths, flickering in and out of existence. In the space outside the plates, anything goes. But the space between the plates acts like a resonant cavity. Only virtual photons whose wavelengths fit neatly into the gap are allowed to exist there. A wave that's too long, for instance, simply can't form. Think of it like a guitar string. It can only vibrate at specific frequencies, its fundamental note and its overtones. All other vibrations are suppressed. The gap between the plates does the same thing, but for the vibrations of the quantum vacuum. The result is that there are fewer, allowed, virtual photons between the plates compared to the infinite space outside. Since each fluctuation carries energy, this means the energy density of the vacuum between the plates is slightly lower than the energy density outside. The universe likes to settle into its lowest energy state. A higher energy density means higher pressure. Therefore, the seething vacuum outside exerts a greater pressure than the slightly calmer vacuum inside, pushing the plates together. The force isn't coming from the plates, it's coming from the vacuum. It's the pressure of nothingness made real. For decades, Casimir's prediction was a theoretical curiosity. But in 1997, a landmark experiment by Steve Lamoureux at the University of Washington measured this tiny force, and the results matched Casimir's prediction to within 5%. While earlier experiments had been attempted, this was a highly precise modern confirmation that the virtual particles were real. They exert a real, measurable force. The empty vacuum pushes and pulls. Other, more subtle observations also point to the activity of the vacuum. The Lamb shift, for example, is a tiny energy difference in the hydrogen atom, which is explained by the interaction of the atom's electron with the surrounding vacuum's energy fluctuations. And even more exotic predictions exist. For instance, in the presence of an incredibly strong magnetic field, like around a neutron star, the vacuum itself should bend light in a specific way, an effect called vacuum birefringence. In 2017, astronomers found tantalizing hints of this effect, suggesting that even the fabric of space can be polarized by a magnet, because it isn't truly empty. The evidence is clear. The lie has been exposed. What we call the void is, in reality, one of the most dynamic things in the universe. It's an incredible thought, isn't it? That the nothing all around us is actually a vibrant, energetic something. This is one of the biggest paradigm shifts in the history of science, and once you see it, it changes everything. If your view of the universe has just been turned upside down, consider subscribing. We dive into these reality-bending topics every week, exploring the deepest questions in physics and cosmology. By joining us, you're not just watching videos. You're on a journey to the very edge of what we know. Now, let's get back to it, because the story of nothing has consequences for everything. Cosmic consequences. The energy of the void. So, the vacuum isn't empty. It's filled with a baseline energy, zero-point energy. This isn't just a quantum quirk that pushes tiny plates together. According to Einstein's theory of general relativity, this vacuum energy should have gravity. And it should have a lot of gravity. When physicists first tried to calculate the theoretical energy density of the vacuum, they arrived at a number so stupendously large it's been called the worst theoretical prediction in the history of physics. It's A1 followed by 120 zeros. If the vacuum really had this much energy, its gravitational pull would be so immense that it would have crushed the entire universe into a ball smaller than an atom, moments after the Big Bang. Clearly, that didn't happen. We're here. The universe is huge and expanding. So, for a long time, most physicists assumed some unknown principle must cancel all this energy out, making the total exactly zero. It seemed like an elegant solution. There was just one problem. In 1998, two teams of astronomers were measuring distant supernovae to map the universe's expansion rate. They expected to find the expansion was slowing down, thanks to the gravitational pull of all the matter in the cosmos. They found the exact opposite. The expansion of the universe is accelerating. Something is acting like a form of anti-gravity, pushing spacetime apart. Scientists gave it a name, dark energy. And whatever it is, it's dominant. Current measurements, including those from the Planck satellite, show that this strange energy makes up nearly 70% of everything in the universe. So what is it? The most straightforward explanation is that it is the energy of the vacuum itself. That the zero-point energy is real, it has a gravitational effect, and it's what's driving the cosmic acceleration. This creates a massive puzzle. On one hand, observations of our accelerating universe prove that vacuum energy must have a real, positive, non-zero value. On the other hand, our best theory of the vacuum predicts a value that is 120 orders of magnitude larger than what we actually see. This gap is known as the cosmological constant problem and it's arguably the single biggest mystery in all of fundamental physics. Why is the vacuum energy so incredibly weak compared to the theory, yet not quite zero? Nobody knows. Finding the answer will likely require a full theory of quantum gravity, a theory of everything, that can finally unite the quantum world with the world of gravity. What's certain is that the energy of nothing is not nothing. It is the most abundant form of energy in the cosmos, and its properties will determine the ultimate fate of our universe. It's the engine driving everything apart, potentially leading to a future, trillions of years from now, where the night sky is truly empty. The lie of empty space is a central character in the story of our entire universe. We started with a simple image, the dark, silent emptiness between the stars. A passive backdrop. A stage of nothingness. We've journeyed from the ancient Greeks debating the void, through Newton's clockwork universe, to the seemingly empty halls of the atom. And at every step, we found that what we mistook for nothing was actually something incredibly important. The emptiness. Inside an atom is a battlefield of forces and quantum rules that give our world its solidity. The emptiness. Between the stars is a vibrant, dynamic fabric woven from invisible quantum fields, constantly jittering and fluctuating. This vacuum is a bubbling cauldron of virtual particles, a phantom sea of zero-point energy that exerts real, measurable forces, as proven by the Casimir effect. The biggest lie in physics isn't just a misunderstanding. It's a failure of our everyday intuition. We're so used to our world of solid things and empty air that our brains aren't built to handle the true nature of reality. The truth is that the universe is far stranger, more connected, and more alive than we can possibly perceive. There's no such thing as a true void. There is no absolute nothing. Every cubic centimeter of space, in this room and in the deepest intergalactic void, is humming with a fundamental energy. This energy of nothing holds the keys to the greatest mysteries we face, from the nature of matter to the expansion of the cosmos. The very foundation of our existence is built upon this seething, energetic quantum void. So, the next time you look up at the night sky, don't see the emptiness. See the fields. See the energy. See the potential bubbling away in the darkness. See the most complex and dynamic something we have ever discovered, cleverly disguised as nothing at all. Science just proved nothing is impossible. What is nothing? It's a question that has echoed through philosophy and science for thousands of years. It's a concept simple enough for a child to grasp, yet so profound it has baffled the greatest minds in history. We think of nothing as absence, as stillness, the ultimate void, an empty box, a silent room, the vast, dark loneliness between stars. For centuries, this idea of a perfect, absolute emptiness has been our baseline for reality, the canvas on which everything else is painted, the zero from which all numbers begin. But what if this fundamental assumption, this bedrock of our intuition, is wrong? What if the very concept of nothing is a cosmic myth? For centuries, we've been haunted by a single, simple idea: nothing. A perfect, absolute void. But what if I told you that science has now proven this idea is a cosmic myth? That the most empty place you can imagine is actually a raging sea of energy and activity? Join us as we explore the ground state of the universe and discover why nothing is the most powerful and misunderstood something in all of existence. The illusion of emptiness. To begin, let's start with a thought experiment you've probably done before. Imagine a box. A perfectly sealed, indestructible box. What would you have to do to make it truly empty? First, you'd remove all the air. Here on Earth, that box is filled with a churning mix of nitrogen, oxygen, and other gases. Trillions of molecules bouncing around, a bustling metropolis of particles. So, clearly, it isn't empty. We attach a vacuum pump to give the molecules an escape route. The best laboratory vacuum chambers, marvels of modern engineering, can reduce the number of particles dramatically. They use high-tech turbomolecular pumps that spin at thousands of RPMs, batting molecules out of the chamber, followed by cryopumps that freeze the stragglers onto an ultra-cold surface. But even then, we can't get every molecule out. Some stubbornly cling to the walls in a process called outgassing. Scientists bake the chambers at high temperatures to force these hidden particles out before sealing them. Despite these heroic efforts, the best vacuums we can create still contain hundreds of particles per cc. Nature's vacuum in deep space is far emptier. But let's imagine we did it. We've built the perfect pump and ejected every last atom. Is the box empty now? Not even close. Our universe is saturated with radiation light from our sun, distant stars, and galaxies. These packets of energy, called photons, are constantly streaming through our box. To get rid of them, we'd have to make the box perfectly shielded from all outside sources. Even then, a more fundamental problem remains. The entire universe is bathed in a faint glow of microwave radiation. the cosmic microwave background, or CMB. It's the oldest light in the universe, the primordial afterglow of the Big Bang itself. It is everywhere, and it is most certainly inside our box. To get rid of that, our box would need to be cooled to a temperature infinitesimally close to absolute zero, -273, 15 degrees Celsius. At this temperature, the walls of the container itself would stop generating their own thermal photons. But achieving absolute zero is forbidden by the laws of thermodynamics. You can get incredibly close, but you can never quite reach it. So, let's grant ourselves another miracle. We've removed every particle, blocked every photon, and cooled our box to absolute zero. Now, surely, we have achieved nothing. The box contains no matter, no light, no heat, a perfect void. Right? Wrong again. This is where we leave intuition behind and enter the strange, fantastic world of quantum mechanics. And this is where science shows us that our very definition of empty is flawed. Peeling back the cosmic onion. The realm of fields. To understand why our perfect box is still not empty, we need to update our idea of what the universe is made of. We used to picture reality as tiny, solid particles zipping around in empty space, like marbles on a table. But modern physics paints a very different picture. The most fundamental things in the universe aren't particles. They're fields. Think of a magnetic field. You can't see it, but you know it's there. Sprinkle some iron filings, and they trace invisible lines of force. The field is a property of space itself. Gravity works the same way. The Earth warps the space-time around it, creating a gravitational field, and we are all just moving along the contours of that warped space. Quantum field theory, our best description of reality, says that everything is a field. For every type of particle, there's a corresponding field that permeates all of space and time. There's an electron field, a photon field, a gluon field, and so on. What we think of as particles are just localized vibrations, excitations in these fields. Imagine a calm pond. The water is the field. If you tap the surface, you create a ripple that travels outward. That ripple is like a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. When these ripples meet, they interact. That's how all forces in the universe happen. These fields aren't just math tricks. They're the fundamental substance of reality. They are woven into the fabric of the cosmos. You can't remove them from our box any more than you could remove space itself. When we thought we were emptying our box, we were just calming down the ripples. We didn't remove the water. The fields are still there. And here's the core of the issue. In classical physics, a field could be perfectly still, with zero energy. The ground state, the state of lowest possible energy, would be perfect nothingness. But the universe isn't classical. It's quantum. And in the quantum world, perfect stillness is forbidden. The heart of the matter. Quantum jitters. This is where we meet one of the pillars of quantum mechanics. The Heisenberg Uncertainty Principle. It states that there's a fundamental limit to how precisely we can know certain pairs of properties at the same time. The more you know a particle's position, the less you can know its momentum, and vice versa. It's not a limit of our tools, it's an inescapable fuzziness built into reality. But another version of this principle relates energy and time. It says you can't know the exact energy of a system over an infinitesimally short period. This creates a kind of cosmic loophole. For very, very short moments, energy can be borrowed from the vacuum, as long as it's paid back almost instantly. Now, let's go back to our empty box, which we now know is filled with quantum fields in their ground state. Classically, this state would have exactly zero energy. But the uncertainty principle says no. If the energy were exactly zero, its uncertainty would be zero, which would violate the principle. Because of this, the energy of a quantum field at any single point can't be perfectly and constantly zero. Instead, it must fluctuate. It jitters. The ground state of a quantum field isn't placid stillness but a seething cauldron of activity. This is known as asterisk quantum fluctuation or asterisk vacuum fluctuation. Think of the ocean's surface. From a great height, it looks perfectly flat, that's the average energy. But zoom in, and you see a chaotic mess of tiny waves, constantly forming and disappearing. The quantum vacuum is the same. It is the lowest possible energy state, but that state is not zero. It's a non-zero minimum, a hum of zero-point energy that can never be silenced. This is the ultimate reason our box can never be empty. Even after we've removed every particle and shielded it from all energy, the fundamental fields of reality itself are still there, forced by quantum law to constantly churn. The void isn't empty. The void is alive. Virtual particles. Ghosts in the machine. So, what do these vacuum fluctuations look like? Physicists often describe this in a way that sounds like science fiction. The constant creation and annihilation of asterisk virtual particles. Because energy and mass are equivalent. Thanks to E equals mc squared, an energy fluctuation can briefly manifest as a pair of particles, a particle and its antiparticle. For an impossibly short moment, an electron and a positron can burst into existence from nothing, existing on borrowed energy. Then, just as quickly, they collide, annihilate each other, and disappear, paying back the energy loan. These aren't real particles in the sense that we can't just catch them. That's why they're called virtual. It's better to think of them as the ripples on the quantum field we talked about, transient disturbances rather than solid objects. The term is a powerful way to picture the unceasing activity of the vacuum. Space, at its most fundamental level, is a chaotic blizzard of these phantom particles, flickering in and out of existence. Virtual photons, virtual electrons, virtual quarks, all part of a restless cosmic dance. The vacuum isn't a silent stage, it's a non-stop rave of ghostly matter and antimatter. This might seem like a wild fantasy. If we can't detect them directly, how do we know they're real? The answer is that while we can't see the individual virtual particles, we can see their collective effects. They leave fingerprints, measurable, predictable fingerprints that provide some of the most powerful proofs we have for the bizarre reality of the quantum world. Now, let's look at the hard proof that this seeming fantasy is an undeniable fact of our universe. The implications have reshaped our understanding of everything from atoms to black holes. If you're enjoying this journey into the true nature of reality, take a moment to subscribe and click the bell icon so you don't miss what's next. Your support helps us tackle these huge questions. The evidence: fingerprints of the void. For a long time, the idea of a seething quantum vacuum was just a theory. But science demands evidence. And in the mid-20th century, that evidence started pouring in. Exhibit A. The Lamb shift. The first major proof came in 1947 from Willis Lamb and Robert Rutherford. At the time, our best theory predicted that two specific energy levels in a hydrogen atom should have exactly the same energy. But when Lamb and Rutherford probed the hydrogen atom with incredible precision, they found this wasn't true. One of the energy levels was slightly higher than the other. The difference was tiny, but it was there, and existing theory couldn't explain it. The explanation came from the quantum vacuum. An electron orbiting a nucleus isn't traveling through a peaceful void. It's swimming through that chaotic sea of virtual particles. This constant jostling smears out the electron's position slightly, altering its energy. Because the two orbitals have different shapes, the electrons in them interact with the vacuum differently. This results in a tiny energy difference, precisely what Lamb measured. It was the first tangible proof that vacuum fluctuations are real, earning Lamb a Nobel Prize in 1955. Exhibit B. The Casimir effect. An even more dramatic confirmation came in 1948 from Dutch physicist Hendrik Casimir. He made a bizarre prediction. Imagine taking two perfectly flat, uncharged metal plates and placing them parallel in a perfect vacuum, just microns apart. Classically, nothing should happen. But Casimir predicted they would be pushed together by an invisible force. His reasoning was elegant. In the open space outside the plates, virtual photons of all possible wavelengths can exist. But the tiny space between the plates acts as a resonant cavity, restricting which virtual photons can pop into existence. Only those with wavelengths that fit neatly into the gap are allowed. This means there are fewer vacuum fluctuations between the plates than outside them. The greater energy of the vacuum outside literally pushes the plates together. This force from nothing is called the Casimir effect. It was finally measured in 1997, and the force matched Casimir's prediction almost perfectly. This is a real, measurable force generated by the energy of empty space. Exhibit C. Modern experiments and beyond. The evidence doesn't stop there. The bare charge of an electron is shielded by a cloud of virtual particles, giving it the finite charge we measure. In the LIGO experiment, which detects gravitational waves, quantum noise from vacuum fluctuations is a factor that engineers must account for in their ultra-precise measurements. In 2024, scientists announced they had finally gathered the first experimental evidence of a related phenomenon called false vacuum decay. Using a supercooled gas just a millionth of a degree above absolute zero, they created an analog of an unstable vacuum and were able to watch as bubbles of a true, lower energy state formed and expanded, driven by thermal fluctuations. This confirmed a key theoretical process believed to be vital to the early universe. Future experiments aim to use powerful lasers to manipulate the vacuum directly, hoping to cause detectable changes in light passing through empty space. From the energy of a single atom to the force between two plates, the evidence is overwhelming. The vacuum is not a void. It's a physical entity, buzzing with energy that has real effects. Cosmic consequences. The reality of vacuum energy isn't just a curiosity. It has startling implications for the entire universe. Black holes and Hawking radiation. In 1974, Stephen Hawking realized that vacuum fluctuations at the edge of a black hole's event horizon would lead to a startling effect. If a virtual particle pair is created there, one particle might fall in while the other escapes. To an outside observer, the black hole has just lost an infinitesimal amount of mass and emitted a particle. This process, now known as Hawking radiation implies that black holes are not completely black. They glow faintly. This effect is incredibly slow, but it means that over unimaginable timescales, every black hole in the universe should eventually evaporate, ultimately destroyed by the energy of nothing. The birth and fate of the universe. Dark energy. Perhaps the biggest implication relates to the expansion of the universe. In 1998, astronomers discovered that the universe's expansion isn't slowing down, it's accelerating. Something is pushing space-time apart, a mysterious force dubbed dark energy. One of the leading candidates for dark energy is vacuum energy itself. According to Einstein's general relativity, the energy inherent in the vacuum should have a gravitational influence, a constant, repulsive force that pushes space apart. This sounds exactly like dark energy. It suggests the fate of our cosmos is being driven by the microscopic jitters of empty space. However, there's a colossal problem, known as the vacuum catastrophe. When physicists try to calculate how much vacuum energy there should be, the number they get is 10 to the power of 120 times larger than what we observe. That's a 1 followed by 120 zeros, the single worst theoretical prediction in the history of physics. If it were that strong, the universe would have ripped itself apart instantly. Something must be canceling out almost all of this energy, leaving just a tiny remnant. Solving this puzzle is one of the biggest open questions in all of science. We began with a simple question: what is nothing? We tried to empty a box, peeling back the layers of reality in a search for the void. And at every turn, we failed. We found that when all matter and radiation are gone, space itself remains, woven from fundamental quantum fields. The laws of quantum mechanics forbid these fields from ever being still. Their lowest energy state, the vacuum, is a cauldron of roiling energy and virtual particles. This isn't speculation. It's a reality proven by experiment. We see its effects in the energy of an atom, we measure its force pushing mirrors together, and we see its signature written across the cosmos, from dying black holes to the accelerating expansion of the universe itself. The simple, intuitive idea of nothing, a perfect, absolute void, is a myth. Science has shown it's impossible. The universe, at its most fundamental level, refuses to be still. It refuses to be empty. The ground state of reality is not absence, but a state of boundless, seething potential. So, the next time you look up at the night sky, at the vast, dark emptiness between the stars, remember what you've learned. That darkness isn't empty. That silence isn't still. It is a stage, filled with an invisible, chaotic dance of energy that has raged since the beginning of time. It is the ultimate proof that in our universe, even nothing is definitively something. Thank you for joining us on this deep dive into the quantum vacuum. If this journey blew your mind, please share it with someone who might appreciate it. There are so many more mysteries to uncover, from dark matter to the inside of a black hole. Subscribe for more explorations into the science that is changing our view of the universe. Until next time, stay curious. The universe's secret hum that prevents nothingness. What is nothing? It sounds like a simple question. We use the word all the time. There's nothing to eat. I'm doing absolutely nothing today. We think of it as an absence, a void. But what if we've been thinking about it all wrong? For centuries, thinkers have imagined perfect, absolute emptiness. An infinite, silent, dark expanse, with no matter, no energy, not even the rules that run the universe. It's the ultimate end, the final state of stillness the universe could one day reach. But what if I told you that nothing is actually the most powerful something in the entire cosmos? What if this idea of a perfect void isn't just hard to find, but is fundamentally impossible? What if the universe itself just won't allow it? We think of empty space as, well, empty. We imagine the coldest possible temperature, absolute zero, as the point where all motion just stops. But that's not right. Even in the deepest, darkest, coldest corner of reality you can picture, a mysterious energy is always humming away. It's a constant, secret buzz. An energy that prevents the universe from ever truly being empty. A cosmic law that guarantees there is always, and will always be, something. This isn't philosophy anymore. This is physics. This is the story of zero-point energy, the universe's fundamental floor, the baseline thrum of activity that proves true nothingness can't exist. It's a story that starts with common sense and ends up at the very edge of what we know, revealing a universe that simply refuses to be silent. To understand this secret hum is to understand why the universe is here at all. The myth of nothing. For most of history, the idea of nothingness was a topic for philosophers, not scientists. The ancient Greeks couldn't agree on it. Some, like Parmenides, argued that nothing couldn't exist because the moment you think or talk about it, you've made it a something. It was a logical trap. Aristotle, one of the most influential thinkers ever, took it a step further. You've probably heard the phrase, "Nature abhors a vacuum." That was him. He just couldn't imagine a place with no substance. To him, space was filled with something, always. If you somehow cleared a region of all matter, he argued, the surrounding stuff would instantly rush in to fill the void. This idea dominated science for nearly 2,000 years. The universe was a full, cozy place, and nothingness was just a spooky story. This classical view pretty much carried over into the age of Isaac Newton. Newton's universe was a magnificent clockwork machine. Planets moved in predictable orbits, and everything followed precise, definite laws. In this clockwork cosmos, there was room for emptiness. Space could be a vacuum, a passive stage for matter and energy to perform on. But it was a quiet stage. If you took a box and removed all the matter, all the light, all the heat, what's left? According to classical physics, nothing. Absolute, static, silent nothing. The peak of this idea was the concept of absolute zero. Temperature is really just a measure of how much atoms and molecules are moving. Heat is just their kinetic energy, they're jiggling and bouncing. The colder it gets, the slower they move. So, logically, there must be a point where all that motion just stops. A temperature so cold that every atom is frozen in place. That point is absolute zero. 0 Kelvin, or minus 273.15 Celsius. At that temperature, the classical universe would be perfectly still. No energy, no movement, no change. This was thought to be the truest form of nothingness you could get. For a long time, this was the accepted picture. The universe had a basement, a ground floor of existence, and that floor was at zero. It was neat, tidy, and made sense. And it was completely wrong. The jump from that classical picture to what we know now was one of the biggest upheavals in the history of science. It didn't just add new details, it tore up the old rulebook. It started in the early 20th century, when strange experimental results started piling up that the old physics just couldn't handle. The clockwork universe was starting to crack, and through those cracks, a much, much weirder reality started peeking through. A reality where stillness was forbidden and emptiness was full. That revolution had a name: quantum mechanics. The quantum revelation. To see why true nothingness is impossible, we have to leave the familiar world behind and step into the strange, bizarre realm of the quantum. This is a world where particles can be in many places at once and where just looking at something changes it. The journey started with light. Is it a wave, or is it a particle? The famous double-slit experiment gave a baffling answer. It's both. And so is everything else. Electrons, protons, the building blocks of you and me, they all have this weird, wave-particle duality. This discovery blew up the classical idea of particles as tiny, predictable billiard balls. Instead, quantum mechanics describes a particle with a wave function, basically, a cloud of possibilities. The cloud tells you where a particle might be, but until you look, it doesn't have a single position. It's in a superposition of all its possible locations at once. This fundamental weirdness, this built-in fuzziness of reality, is the key. And it's all wrapped up in one of the most profound ideas in all of science: the Heisenberg Uncertainty Principle. Developed by Werner Heisenberg in 1927, the uncertainty principle sets a hard limit on what we can ever know about a particle. The famous version says you can't know both the exact position and the exact momentum of a particle at the same time. Think of it this way. To see where a particle is, you have to bounce something off it, like a photon of light. But that very act gives the particle a kick, changing its momentum. The more precisely you want to measure its position, the harder you have to hit it, and the more you mess up its momentum. Now, this isn't just because our tools are clumsy. It's not a limitation we can fix with better tech. The uncertainty is a fundamental, baked-in feature of the universe. A particle simply doesn't have a perfectly sharp position and momentum at the same time. So, what does this have to do with absolute zero and nothingness? Everything. Remember that classical idea of a particle at absolute zero? It's perfectly still. That means its momentum is exactly zero. But if its momentum is zero, the uncertainty principle says its position must be infinitely uncertain. It could be anywhere in the universe. Flip it around. Let's say we pin the particle down to a specific spot. Now we know its position perfectly. But if we do that, the uncertainty principle says its momentum must be infinitely uncertain. It can't possibly be at rest. It has to be jiggling around like crazy. It's a paradox with no escape. The state of absolute rest, a particle with zero momentum at one specific location, is physically impossible. It breaks the fundamental rules of quantum mechanics. A particle can never be perfectly still. It must always have a little bit of residual motion, a fundamental jiggle. Even at absolute zero, this quantum jitter remains. This is the first crack in the idea of nothingness. But the uncertainty principle has an even weirder implication. There's another version of the principle that relates energy and time. It says that the shorter the period of time you look at something, the more uncertain its energy is. Now, think about a perfect vacuum, truly empty space. Classically, its energy is zero. Period. But according to the uncertainty principle, to be absolutely sure the energy is zero, you'd have to measure it for an infinite amount of time. Over any real-world time span, no matter how short, there's a built-in uncertainty to the energy of that empty space. This means the energy of the vacuum can, and does, fluctuate. For incredibly brief moments, energy can just appear from nowhere, as long as it disappears again fast enough. And since Einstein's E equals mc squared tells us that energy and mass are two sides of the same coin, these energy fluctuations can show up as particles. Out of the nothingness, pairs of virtual particles, a particle and its antimatter twin, pop into existence, exist for a fleeting moment, and then annihilate each other, paying back their energy loan to the void. This isn't a rare event. It's happening everywhere, all the time. The vacuum of space, what we thought was the definition of empty, is actually a seething, bubbling soup of these phantom particles. A quantum foam. This is the quantum revelation. It tells us that on the most basic level, reality is not fixed, but constantly churning. It says absolute stillness is forbidden and that even the most perfect vacuum is a beehive of activity. This baseline, irreducible energy that exists everywhere, even at absolute zero, is the universe's secret hum. It is zero-point energy. The universe's hum, zero-point energy, or ZPE, is the lowest possible energy a quantum system can have. It is the absolute ground floor of existence. And thanks to the uncertainty principle, that floor is not at zero. The idea first came from people like Max Planck, Albert Einstein, and Otto Stern. They realized that even at absolute zero, the tiny oscillators that make up matter would still hold on to a tiny bit of residual energy. This wasn't leftover heat. It was a fundamental property of being a quantum object. Quantum field theory takes this idea and runs with it. In this view, the universe is filled with fields: an electron field, a photon field, and so on. A particle is just a little ripple, an excitation, in its corresponding field. Zero-point energy is the energy of these fields when they're in their resting state, when no real particles are around. When you add up all the ZPE for all the fields at every single point in space, you get a wild conclusion. The vacuum itself has an immense amount of energy. For a long time, many physicists treated ZPE as a mathematical quirk that could be ignored in calculations. But what if this energy was real? How could you ever prove that an energy that's everywhere, all the time, actually exists? The answer came in 1948 from Dutch physicist Hendrik Casimir. He came up with a brilliant thought experiment to provide real, measurable proof of zero-point energy. This is the Casimir effect. Imagine two perfectly flat, uncharged metal plates in a perfect vacuum, placed incredibly close to each other. Classically, nothing should happen. They're just sitting there. But Casimir realized the quantum vacuum would have something to say about this. Remember those virtual particles popping in and out of existence? They correspond to electromagnetic waves of all possible wavelengths. Outside the plates, waves of all sizes can exist. But the tiny gap between the plates acts like a filter. Only virtual photons whose wavelengths fit neatly into that gap are allowed. This means there are fewer possible quantum fluctuations, fewer virtual particles between the plates than outside them. The zero-point energy is lower inside the gap than it is in the surrounding space. This imbalance creates a pressure. The greater energy of the vacuum outside literally pushes the plates together. This tiny, subtle force, coming from the nothingness of space, is the Casimir force. For decades, this was just a wild idea. The force was predicted to be so tiny, how could you ever measure it? But scientists are persistent. After years of attempts by others, the effect was finally confirmed with incredible precision in 1997 by physicist Stephen Lamoureux. His results matched Casimir's prediction almost perfectly. Since then, the experiments have gotten even better, leaving no doubt. The Casimir effect is real. The hum of the universe is real. And it can push things around. The Casimir effect is maybe the most direct proof, but it's not the only one. There's the Lamb shift. In the 1940s, Willis Lamb was taking super precise measurements of the hydrogen atom and found a tiny energy difference between two electron orbitals that, according to theory at the time, should have been identical. The explanation? Zero-point energy. The endless fluctuations of the vacuum jiggle the electron just enough to shift its energy level by a tiny, but measurable, amount. And you can even see the effects on a larger scale. Take the element helium. As you cool it down, you'd expect it to freeze solid, like anything else. But helium just refuses. At normal pressure, even as you get ridiculously close to absolute zero, it stays liquid. Why? Zero-point energy. The helium atoms are so light that their fundamental quantum jiggle is powerful enough to overcome the weak forces that would normally lock them into a solid crystal. The atoms are just too restless to freeze. To make solid helium, you have to apply over 25 times normal atmospheric pressure to force them together. Even weirder, if you cool helium-4 below about 2 Kelvin, it becomes a superfluid, a liquid that flows with zero friction and can even crawl up the walls of its container. This is a direct, large-scale consequence of all the atoms settling into their lowest possible energy state, a state completely dominated by their zero-point energy. From a tiny force between two plates, to a flicker of light from an atom, to a liquid that won't freeze, the evidence is everywhere. Zero-point energy isn't a fantasy. It's a real, measurable, and powerful part of our universe. it's one of those ideas that really sticks with you, isn't it? That empty space isn't empty at all. If you enjoy having your brain twisted into a pretzel like this, you're in the right place, so maybe think about subscribing. I genuinely want to know what you think. Does this idea of a quantum nothing make sense to you? Let me know down in the comments. I read them all, and that's where some of the best ideas for new topics come from. Alright, let's get back to it and see what this all means for the fate of the entire universe. The cosmic implications. The discovery that the vacuum is actually an ocean of energy has consequences that stretch from the smallest particles to the largest structures in the cosmos. The universe's secret hum might just be the key to some of the biggest mysteries we're facing. The most famous connection is to the puzzle of dark energy. In the late 1990s, astronomers found something shocking. They assumed the expansion of the universe was slowing down, pulled back by the gravity of all the stuff in it. They found the exact opposite. The expansion of the universe is accelerating. Something is acting like a kind of anti-gravity, pushing spacetime itself apart, faster and faster. This mysterious stuff was named dark energy, and it seems to make up about 70% of the entire universe. But what is it? The leading suspect is the energy of the vacuum itself, the very zero-point energy we've been talking about. It seems like a perfect match. There's just one giant, colossal problem. It's often called the worst prediction in the history of physics. When physicists try to calculate how much energy the vacuum should have based on quantum theory, they get an answer that is comically, horrifyingly wrong. The predicted value is about 10 to the power of 120 times larger than the value we actually observe. That's a 1 followed by 120 zeros. It's a discrepancy so huge it's hard to even describe. It's like measuring a wooden ruler and predicting it should be long enough to stretch across the entire observable universe. This is the cosmological constant problem, and it's one of the deepest mysteries in all of science. Something is deeply wrong with our understanding. Is there some unknown physics that cancels out almost all of this energy? Do our theories of quantum mechanics and gravity just not play nice together? We don't know. The cosmological constant problem shows us that while we know the hum is real, it holds secrets we have yet to even guess at. The implications don't stop there. ZPE even touches on the beginning of the universe. The big question has always been, how do you get something from nothing? The Big Bang Theory is great at explaining how the universe evolved, but not where the initial hot, dense state came from. Quantum fluctuations offer a wild possibility. If the vacuum isn't nothing, but a quantum foam bubbling with potential, then maybe our entire universe is the result of one giant quantum fluctuation. In this picture, the nothing before the Big Bang wasn't a void, but a quantum vacuum. A random fluctuation could have brought our universe into existence. This idea is sometimes called a universe from nothing, but that's not quite right. It's a universe from quantum nothing, which, as we've seen, is very much a asterisk something. Finally, ZPE even changes how we think about black holes. Stephen Hawking showed that black holes aren't truly black. Thanks to quantum fluctuations at their edge, the event horizon, they slowly radiate particles away and evaporate over unbelievable timescales. This Hawking radiation is basically the black hole's mass being converted into energy, powered by the zero-point fluctuations of the vacuum. It suggests that even in the face of absolute gravitational collapse, the quantum hum persists, ensuring that no part of the universe is ever truly silent or cut off forever. From the acceleration of the cosmos to the birth of the universe and the death of black holes, zero-point energy is woven into the fabric of reality at every scale. The fact that we don't fully understand it just makes it more important. It tells us that locked inside the hum of the void is the key to a much deeper picture of our universe. So, where does all this leave us? We started with a simple question, what is nothing? And ended up rewriting the fundamental rules of reality. We've seen that the laws of nature themselves, through the Heisenberg Uncertainty Principle, forbid perfect emptiness and absolute stillness. At every single point in space, there is a fundamental, irreducible energy. The zero-point energy. This isn't just a theory. We see its effects. We see it in the Casimir force pushing plates together. We see it in the Lamb shift, subtly changing the light from an atom. We see it in superfluid helium, a liquid that's too restless to freeze. This cosmic hum is the universe's baseline. It's the floor that reality can't drop below. It tells us that a state of absolute nothingness isn't just something we can't reach, but that it's an impossibility in our quantum world. The vacuum isn't empty. It's a stage of infinite potential, from which particles can spring and from which the universe itself may have been born. We're left with a universe that is profoundly different from the one we imagine. It's a place where emptiness is full, where stillness is in constant motion, and where silence is a symphony of quantum jitters. The great mystery that's left the cosmological constant problem is a giant signpost pointing toward the next great revolution in physics. So, the next time you look up at the night sky, at the vast, dark expanse between the stars, remember what you now know. That darkness isn't empty. That silence isn't still. It is humming with a secret energy. It is alive with the potential of everything that is, and everything that could ever be. The universe refuses to be silent. It insists on existing. And because of this fundamental, inescapable hum, there will never, ever be truly nothing. There will always be something. And that might be the most beautiful mystery of all. The universe's secret hum, why reality can never be still. It's the most natural feeling in the world, isn't it? Stillness. That quiet pause between breaths. The heavy silence of a library, thick with unspoken thoughts. The cold, dark, empty space between the stars. We tend to think of reality as a stage, where things happen against a backdrop of absolute calm, a canvas of perfect nothingness where the drama of existence unfolds. It feels like there are gaps everywhere, a dark, silent canvas on which the universe places its stars. We look at a mountain and see an icon of permanence, an object so still it's become a metaphor for immovability itself. We crave stillness, we seek it out in meditation and in the quiet moments of the early morning. It feels like the universe's default state, the baseline from which all motion, all noise, all life, begins. But it's all an illusion. Because for nearly a century, physics has been uncovering a secret. A fundamental law, written into the very fabric of the universe, that forbids true silence. A law that says even in the coldest, darkest vacuum, reality can never, ever be still. Physics has a habit of gently, and sometimes violently, undoing what feels obvious. It's told us that solid ground is mostly empty space, that time can stretch and shrink, and that a cat can be both alive and dead. But perhaps its most profound revelation is this. The universe is built not on a foundation of stillness, but on a restless, ceaseless, creative energy. A secret hum that prevents reality from ever truly being quiet. To understand this hum is to understand why the universe is the way it is, dynamic, evolving, and always in motion. The cosmic dance. Our illusion of stillness starts to crumble the moment we zoom out. You might feel perfectly still right now, sitting in a chair, but you are anything but. You're a passenger on a colossal cosmic vessel, and it's moving at speeds that are almost impossible to comprehend. Let's start with the motion we know best, the one that gives us our days and nights. The Earth is spinning on its axis, a great planetary pirouette. If you're at the equator, this rotation is carrying you through space at over 1,600 kilometers per hour faster than the speed of sound. You don't feel it because everything around you, the chair, the room, the atmosphere itself, is moving right along with you, a shared momentum that creates a local illusion of rest. But that's just the first step in a much grander dance. As it spins, the Earth is also hurtling through space in its orbit around the Sun. To stay tethered to our star, our entire world is careening along its orbital path at a staggering 107,000 kilometers per hour. In the time it takes you to watch this video, you will have traveled thousands of kilometers through the solar system. Every year, you complete a journey of nearly 1 billion kilometers, only to end up right back where you started, ready to do it all over again. And yet, this solar system, which feels so vast and central to our existence, is itself just a tiny raft adrift in a far greater river of motion. Our Sun, along with all its planets, comets, and asteroids, is just one of hundreds of billions of stars that make up the Milky Way galaxy. And this entire galactic structure isn't static. It's a spinning, spiraling vortex of stars, gas, and dust. Our solar system is located in one of its spiral arms, about 2/3 of the way out from the galactic center. And we are being dragged along in a majestic orbit around the supermassive black hole that sits at the galaxy's heart. This galactic journey is almost beyond imagination. Our solar system is moving at an average speed of 828,000 kilometers per hour. Even at this insane velocity, it'll take us about 230 million years to complete just one orbit around the Milky Way. Dinosaurs were roaming the Earth the last time our solar system was in this same part of the galaxy. The cosmic dance, however, doesn't stop there. The Milky Way isn't alone in the universe. It's part of a local cluster of galaxies known as the local group. And this entire group, a collection of over 50 galaxies including the Great Andromeda Galaxy, is falling through space. Pulled by the immense gravity of something far larger, our entire galactic neighborhood is on a trajectory. We're being pulled toward the Virgo cluster, a massive collection of thousands of galaxies. But even that isn't the final destination. The Virgo cluster, our local group, and countless other galaxies and groups are all part of an even more colossal structure: the Laniakea supercluster. Laniakea, a Hawaiian name meaning immense heaven, is one of the largest structures in the known universe, a sprawling cosmic web of 100,000 galaxies stretching over 520 million light-years. And deep within this supercluster lies a gravitational anomaly, a place where the fabric of spacetime is so warped by an unseen concentration of mass that it pulls everything, our galaxy included, toward it. It's known as the Great Attractor. Our Milky Way is hurtling towards this enigmatic point in space at a mind-bending 2 million kilometers per hour. And finally, the entire canvas of reality is itself in motion. Ever since the Big Bang, the fabric of spacetime has been expanding. Every supercluster is moving away from every other supercluster. The universe is getting bigger every single second. So, stillness is a lie. From the spin of our planet to the fall of our galaxy toward the Great Attractor, to the expansion of the universe itself, everything is in a state of perpetual, frantic motion. There is no fixed point, no absolute here, in the cosmos. We are all cosmic wanderers. This leads to a profound question. We see motion on every grand scale we can observe. But is this motion fundamental? Or is it just the leftover energy from a chaotic beginning? What happens if we try to escape it? What if we zoom in, past the planets, past the atoms, into the realm of the truly small? What if we travel to the coldest, emptiest void we can imagine? Can we, there, finally find a place where reality is truly still? Our classical intuition, the gut feeling built from our everyday world, would say yes. If you remove all the energy from a system, if you cool it down to the coldest possible temperature, it should become perfectly still. But as we journey into the quantum realm, we find that the universe has other plans. The search for stillness. For centuries, the dream of absolute stillness was a logical endpoint for physics. Temperature, we eventually understood, is just a measure of the motion of atoms and molecules. The hotter something is, the more violently its parts jiggle and vibrate. The colder it gets, the more sluggish they become. So, it stood to reason that if you could remove all of the heat, all of the energy, you would arrive at a state of perfect calm. This theoretical point of ultimate cold was given a name: absolute zero. It's zero on the Kelvin scale, which is minus 273.15 degrees Celsius. At this temperature, according to the old laws of classical physics, all particle motion should just stop. Atoms would stop vibrating. Electrons would stop orbiting. Everything would be frozen in a state of perfect, crystalline stillness. The universe, in that one isolated spot, would finally hold its breath. This idea was so intuitive that it became a foundation of thermodynamics. The pursuit of absolute zero became a kind of holy grail for physicists in the 19th and early 20th centuries, a race to the very bottom of the thermometer. But at the dawn of the 20th century, the first cracks in this classical dream started to appear. And they came from a place no one expected: the simple glow of a hot object. The problem was known as black body radiation. Scientists were trying to create a formula that could predict the spectrum of light, the different colors and intensities emitted by a perfect absorber of radiation. The problem was, classical physics predicted that as the frequency of light increased into the ultraviolet range, the energy emitted should skyrocket to infinity. This was a catastrophic failure of theory, so absurd it was nicknamed the ultraviolet catastrophe. Clearly, something was deeply wrong with the physics of the day. In 1900, a German physicist named Max Planck, a man who was by his own admission a pretty conservative thinker, reluctantly proposed a radical solution. He suggested that energy wasn't continuous. It couldn't be released in just any old amount. Instead, he argued, energy could only be emitted or absorbed in discrete, tiny packets, which he called quanta. The energy of each quantum was directly tied to the frequency of the radiation. Planck himself was deeply troubled by his own idea, viewing it as just a mathematical trick to make the equations work. He didn't believe it reflected some fundamental truth about nature. But his formula worked perfectly. He had accidentally stumbled upon the foundational pillar of a new reality. The universe, at its most fundamental level, wasn't smooth and continuous, but grainy and quantized. The age of quantum mechanics had begun. This idea of quantization slowly began to reshape physics. In 1905, a young patent clerk named Albert Einstein used Planck's idea to explain the photoelectric effect, showing that light itself behaves like it's made of these energy packets, which we now call photons. In 1913, Niels Bohr applied it to the atom, proposing that electrons could only exist in specific, quantized energy orbits, which neatly explained the mysterious spectral lines of elements. But the full, breathtaking weirdness of the quantum world was yet to be unveiled. And it would be another young German physicist, Werner Heisenberg, who would deliver the final, fatal blow to the dream of absolute stillness. In 1925, suffering from a nasty case of hay fever, the 23-year-old Heisenberg retreated to the barren, pollen-free island of Heligoland. There, surrounded by sea and rock, he wrestled with the bizarre behavior of electrons. He abandoned the idea of even trying to visualize what was happening inside an atom. Bohr's little solar system orbits just weren't cutting it. Instead, he focused only on what could be observed: the light emitted by atoms. He developed a strange new form of math to describe it, a system of arrays of numbers that would later be identified as matrix mechanics. It was abstract and difficult, but it worked. 2 years later, in 1927, while working in Copenhagen with Niels Bohr, Heisenberg uncovered the profound implication of his new mechanics. In a letter to a colleague, he articulated an idea that would become one of the most famous and misunderstood principles in all of science: the Heisenberg Uncertainty Principle. The principle is, at its heart, a statement of a fundamental limit imposed by nature itself. It says there are certain pairs of properties of a particle that you just can't know with perfect, simultaneous accuracy. The most famous of these pairs is position and momentum. The more precisely you measure the position of a particle, the less precisely you can know its momentum. And conversely, the more precisely you nail down its momentum, the fuzzier its position becomes. Now, to be absolutely clear, this isn't a limitation of our measuring tools. It's not that our instruments are too clumsy and disturb the particle. It is a fundamental, baked-in feature of reality. A particle, at the quantum level, doesn't have a single, definite position and a single, definite momentum at the same time. Its very existence is fuzzy. A good analogy is to think of a wave on a pond. A particle, like an electron, has wave-like properties. If you want to measure the momentum of this wave, you need to know its wavelength, the distance between crests. To get an accurate measurement, you need to see a lot of crests pass by. But if you're observing a long train of waves, where exactly is the wave's position? It's spread out. So, a well-defined momentum corresponds to a very uncertain position. Now, what if you want to know the wave's precise position? You'd have to squeeze it into a tiny spot. A wave confined to a tiny spot is just a single, sharp spike. But what's the wavelength of a single spike? It's undefined. It's a jumble of an infinite number of different wavelengths all mashed together. So, a well-defined position corresponds to a completely uncertain momentum. This trade-off is absolute. The product of the uncertainty in position and the uncertainty in momentum must always be greater than or equal to a tiny, but non-zero, number. Planck's constant divided by 4 pi. This is the law that kills the dream of absolute stillness. Think about what it would mean for a particle to be perfectly still. It would need to have a precise momentum of exactly 0. If its momentum is precisely 0, its momentum uncertainty is 0. According to Heisenberg's principle, if the momentum uncertainty is 0, then the uncertainty in its position must be infinite. A particle that is perfectly still would have no location. It would be everywhere in the universe at once. Let's try it the other way. To be still in a specific place, a particle would need to have a precise position. If we pin it down to one exact spot, its position uncertainty is 0. In that case, its momentum uncertainty would have to be infinite. Its velocity could be anything. The very act of confining a particle to a single point guarantees it will be vibrating and jiggling with wild abandon. It cannot be localized and have 0 momentum at the same time. Nature forbids it. This isn't just a philosophical puzzle. It has real, physical consequences. It means that even if you could cool a system down to absolute 0, its particles cannot stop moving. They have to retain a minimum amount of motion, a slight, perpetual jiggle, to satisfy the uncertainty principle. This irreducible, minimum energy that a system has, even at absolute 0, is called the zero-point energy. It is the universe's secret hum. It is the baseline of existence. And this principle has a second, equally profound form. Just as position and momentum are linked, so are energy and time. The more precisely you know the energy of a system, the less precisely you know the duration over which it has that energy. Or, put another way, for very, very short intervals of time, the conservation of energy can appear to be violated. This means that for a fleeting moment, a quantum system can borrow energy from seemingly nowhere, as long as it pays it back very, very quickly. The shorter the time, the more energy it can borrow. And where does it borrow this energy from? It borrows it from the vacuum itself. The void. The nothingness we thought was the bedrock of stillness. It turns out that this nothingness is a roiling, bubbling, energetic place, the true source of the universe's restless heart. The universal hum in action. The uncertainty principle isn't just some abstract mathematical rule. Its consequences are woven into the fabric of the cosmos, creating real effects we can actually measure. The secret hum of zero-point energy isn't a metaphor. It's real. The most direct consequence is the zero-point energy itself. It's the reason that even at absolute zero, matter isn't still. Take liquid helium. When you cool it to just a few degrees above absolute zero, it exhibits bizarre properties. It becomes a superfluid, able to flow without any friction, even climbing up the walls of its container. The reason it doesn't freeze solid, even at the lowest temperatures, is because of zero-point energy. The helium atoms are forced by the uncertainty principle to keep jiggling, a quantum restlessness that prevents them from locking into a fixed, solid crystal lattice. They remain in this strange, fluid state, a macroscopic testament to the universe's inability to be still. But the hum extends beyond matter. It fills the vacuum of space itself. The energy-time uncertainty principle allows for a constant, chaotic dance to occur in what we perceive as emptiness. For incredibly brief moments, pairs of particles can literally burst into existence, borrowing their energy from the vacuum, before quickly annihilating each other and disappearing. These are called virtual particles. An electron and its antiparticle, a positron, can spontaneously emerge from nothing, exist for a time so short it's beyond our ability to directly see them, and then vanish back into the void. This means that empty space isn't empty at all. It's a seething, bubbling foam of potential, a quantum foam where particles are constantly flickering in and out of reality. The vacuum has energy. Its ground state energy is not zero, it's filled with the hum of all these potential particles. This vacuum energy is a direct manifestation of the zero-point field. For a long time, this idea seemed like a fantasy, a ghost in the mathematical machine of quantum mechanics. But in 1948, the Dutch physicist Hendrik Casimir proposed an experiment to prove this vacuum energy was real. His idea was simple and elegant. Imagine you take two perfectly smooth, uncharged metal plates and place them parallel to each other in a perfect vacuum, incredibly close together just a few micrometers apart. Outside the plates, virtual particles of all wavelengths and energies can pop in and out of existence. No restrictions. But between the two plates, things are different. The space is confined. Only virtual photons whose wavelengths fit a whole number of times into the tiny gap can exist there. This means there are more possible virtual particles, more modes of the quantum vacuum on the outside of the plates than on the inside. This imbalance creates a tiny, but measurable, pressure. The greater energy of the vacuum outside the plates actually pushes them together. This force, arising from nothing but the fluctuations of empty space, is known as the Casimir effect. For decades, it was a theoretical curiosity. But in 1996, the effect was finally measured with precision, and the results matched the predictions of quantum theory almost perfectly. It was definitive proof. The vacuum is not empty. The hum is real. The influence of this quantum hum reaches the most extreme corners of the universe, even to the edges of black holes. In 1974, Stephen Hawking was trying to combine quantum mechanics with the general relativity that describes black holes. He realized that the creation of virtual particle pairs right at the event horizon, the point of no return, would have a strange effect. Normally, these pairs annihilate each other almost instantly. But if a pair of virtual particles is created right at the edge of a black hole, it's possible for one particle to fall in, while the other escapes. The particle that falls in has to have negative energy to balance the universe's energy books, which effectively reduces the mass of the black hole. The particle that escapes carries positive energy away into space. To a distant observer, it looks as if the black hole itself is emitting radiation. This phenomenon, now known as Hawking radiation, means that black holes aren't truly black. They glow, though incredibly faintly. Over immense periods of time, trillions upon trillions of years, for a large black hole, this steady leak of energy will cause the black hole to evaporate and eventually disappear in a final burst of radiation. The very existence of black holes, the universe's ultimate symbols of permanence, is ultimately undone by the restless quantum jiggle of the void. So, from the strange behavior of supercooled liquids to the force that pushes two plates together in a vacuum, to the slow death of black holes, the evidence is all around us. Reality is never still. The universe is filled with a fundamental, irreducible energy, a constant hum that prevents perfect silence and perfect stillness from ever taking hold. It is a creative and destructive force, responsible for both the structure we see and the eventual decay of all things. The ideas we've explored today, like the uncertainty principle and zero-point energy, are the bedrock of modern physics. They challenge our intuition and force us to see the world in a completely new light. If you're passionate about digging deeper into the fundamental principles that govern our reality, and want to build a really strong foundation in science and math, there's no better place to continue your journey than Brilliant.org. Brilliant is an interactive learning platform that makes complex topics in science, math, and computer science genuinely accessible and fun. Instead of just passively watching videos, you learn by doing, solving problems and building your intuition one concept at a time. They have an entire course on quantum mechanics that takes you step by step through the principles we've talked about, from wave-particle duality to the uncertainty principle, using these incredibly intuitive visual explanations. It's the perfect way to go from being a curious viewer to someone who truly understands these profound ideas. To support our channel and start your own journey of discovery, you can get started for free. And for a limited time, the first 200 people to sign up using the link in the description will get 20% off an annual premium subscription. By signing up, you're not just investing in your own learning. You're helping us continue to make deep dives into the biggest questions in the cosmos. So click the link and let your curiosity guide you. The music of reality. We began with a simple, relatable feeling. The quiet of a still room, the silent majesty of the night sky. It's an experience that feels fundamental, a sense of peace that comes from the absence of motion and noise. But our journey, from the cosmic dance of galaxies to the frantic jiggle of the quantum realm, has shown us that this feeling is the grandest of all illusions. The stillness you perceive isn't an absence of motion, but a trick of scale. You're standing on a planet that is spinning, orbiting, falling, and fleeing across the cosmos at unimaginable speeds. The silence you perceive isn't an absence of sound, but a harmony so fundamental it slips right beneath the notice of your senses. The universe isn't built on a foundation of stillness, but on a restless, creative energy. This energy, born from the fundamental law of quantum uncertainty, ensures that nothing can ever truly stop. Even in the coldest, emptiest void, at the theoretical limit of absolute zero, there is a persistent hum, a floor of energy from which all of reality emerges. The vacuum is not a void, it's a plenum, a seething ocean of virtual particles flickering in and out of being. This constant motion isn't a flaw in the system. It is the system. It's what allows for the existence of matter, for the stability of atoms, and for the slow, inevitable evolution of the cosmos. Without the uncertainty principle, electrons would spiral into the nucleus of atoms in an instant, and the universe as we know it simply couldn't exist. The fuzziness of quantum mechanics is the very thing that gives reality its substance and its structure. So, the next time you find yourself in a moment of profound quiet, listen closely. Listen past the sounds of your own world, past the beating of your own heart. Listen for the subtle vibration that underpins everything. You are never truly still. You are never in true silence. You are part of a great cosmic symphony, a passenger on an enormous, invisible wave of motion that began billions of years ago and will continue for trillions more to come. Reality can never be still, because at its very heart, the universe is not silence. It is music. The ghost in the universe, what hides in empty space. You've probably heard that atoms are mostly empty space. A tiny nucleus, lost in a vast cloud of probability where an electron might be. We tend to picture the universe as these scattered islands of matter in an infinite ocean of just nothing. Absolute, definitive nothing. But what if that picture is completely wrong? What if empty space is actually the most crowded, chaotic, and dynamic place in the entire cosmos? What if the profound nothingness we imagine between the stars, between atoms, between the very threads of reality, is actually a seething, bubbling cauldron of ghostly particles? Phantoms that erupt into existence from absolutely nowhere, only to vanish just as quickly. What if, because of these ghosts, true and absolute nothingness is a physical impossibility? That the laws of the universe themselves just fundamentally forbid it? What are these phantoms that haunt every single cubic centimeter of space? And what are they telling us about the fundamental nature of reality itself? The answer will change the way you see everything. The illusion of emptiness. To start, we have to agree on what we even mean by nothing. For centuries, this was a question for philosophers. The ancient Greek thinker Democritus imagined a universe made of two things: atoms and the void, indivisible little bits moving through a truly empty expanse. But his contemporary, Aristotle, hated that idea. He believed nature abhors a vacuum, that true emptiness couldn't exist, and that some unseen substance, an ether, had to fill all of space. For over 2,000 years, that was the debate. Is space an empty stage, or is it an active player in the cosmic drama? Let's be honest, our modern intuition totally sides with Democritus. We think of a vacuum as what's left when you take everything away. Imagine a perfectly sealed, indestructible box. We pump out all the air, molecule by molecule. We shield it from all light, every last stray photon. We cool it down to absolute zero, the theoretical point where all classical motion is supposed to cease. So, what's left inside? Common sense tells us nothing. An absolute void. This feeling is reinforced when we look at matter itself. We learn that an atom is over 999% empty space. If you scaled up a hydrogen atom so its nucleus was a marble in the center of a football stadium, its single electron would be a speck of dust zipping around the nosebleed seats. Everything in between? Empty space. You, me, this planet, we're all overwhelmingly made of nothing. It feels like emptiness is the default state of the universe, and matter is just a temporary glitch. But this is where our intuition completely fails us. Because at the dawn of the 20th century, a young patent clerk named Albert Einstein didn't just change the rules, he shattered the entire game board. He showed us that even if you could somehow remove every last particle from our imaginary box, you would not be left with nothing. You'd be left with space. And here's the critical insight: space is not nothing. In Einstein's general relativity, space isn't a passive backdrop. It's a real, physical entity, fused with time into a four-dimensional fabric, spacetime. And this fabric isn't static, it's dynamic. It can bend, stretch, and ripple. What we feel as gravity isn't some mysterious action at a distance, like Newton thought. It's just the shape of spacetime. A planet orbiting a star isn't being pulled by an invisible rope. It's following the straightest possible path through a patch of spacetime that's been warped by the star's mass. Think of it like a bowling ball on a stretched-out rubber sheet. The ball creates a dip. If you roll a marble nearby, it won't travel in a straight line. It'll follow the curve made by the bowling ball. The marble isn't being pulled. It's just moving along the geometry of the surface it's on. This was a massive shift in thinking. Space itself has properties. It has a geometry. And you can't get rid of the rubber sheet itself. You can take the bowling ball and the marble away, but the sheet is still there. Space-time is a fundamental piece of reality. You can remove everything from space, but you can't remove space itself. This was the first major crack in the idea of absolute nothingness. But it was only the beginning. Because another, even weirder theory was about to reveal that this fabric of spacetime was far from quiet. It was haunted. Unveiling the quantum realm. Okay, so empty space is, at the very least, something asterisk. The physical fabric of spacetime. But let's go back to our perfect box, empty, shielded, cooled to absolute zero. No matter. No radiation. Just spacetime. Can we finally say it's empty? This is where the other great pillar of modern physics, quantum mechanics, steps in and says, not so fast. Quantum mechanics runs the universe on its smallest scales, and its rules are deeply weird. One of its most fundamental laws is the Heisenberg Uncertainty Principle. In simple terms, it says there's a hard limit to how much you can know about certain pairs of properties at the same time. The most famous pair is a particle's position and its momentum. The more you pin down exactly where a particle is, the less you can know about where it's going, and vice versa. And this isn't because our tools aren't good enough. The uncertainty is baked into reality itself. A particle doesn't have a single, precise position and momentum. It exists in a fuzzy, probabilistic haze. Now, think about what this means for our empty box. If the box were truly empty, with zero energy, it would be perfectly still. Every point in that space would have exactly zero energy and zero momentum, fixed in place. We would know its position and its momentum with perfect certainty. But that's a direct violation of the uncertainty principle. Reality itself says, nope, you can't have a state of perfect zero. Because of this, even in a total vacuum at absolute zero, there has to be a minimum amount of energy. This irreducible, unremovable energy that fills all of space is called zero-point energy. It's the universe's baseline hum. Even when all the instruments are off and the musicians have gone home, the concert hall of reality is still filled with a faint, ever-present tone. You can't get rid of it. It's the energy of space itself. So, if empty space is filled with energy, what form does that energy take? This is where we get to one of the most beautiful and profound ideas in all of physics, quantum field theory. The modern view is that the most fundamental things in the universe aren't particles. They're fields. Imagine that all of space is filled with a collection of invisible fields. There's an electron field, a photon field, a quark field, a Higgs field, one for every particle that exists. In this picture, particles aren't the fundamental things. They're just excitations, vibrations, or ripples in their fields. An electron isn't an object. It's a localized, vibrating packet of energy in the electron field. A photon of light is a ripple in the electromagnetic field. The fields are the true reality. Particles are just what they do. Picture the universe as a vast, calm ocean. This ocean represents a quantum field, say, the electron field. When the ocean is perfectly flat, there are no particles. No electrons. But if you tap the surface, a ripple spreads out. That ripple, that disturbance of the water, is the particle. That's the electron. The ripple isn't separate from the ocean. It's a behavior of the ocean. Now, you can imagine an ocean with no ripples. But you can't get rid of the ocean itself. The field is always there. But we just learned that these fields can never be perfectly still. They have to contain that zero-point energy. So what are they doing in our empty box? They are fluctuating, vibrating, constantly humming with energy. And here is where the ghost finally appears. These fluctuations aren't just gentle hums. They're wild and chaotic. Thanks to another part of the uncertainty principle that relates energy and time, a field can borrow a bit of energy from the vacuum, as long as it pays it back incredibly quickly. And what can it do with that borrowed energy? According to Einstein's famous E=mc², energy can become mass. So, for an impossibly brief moment, a quantum field can borrow enough energy from the void to create a particle-antiparticle pair. The electron field might suddenly fizz, creating an electron and its antimatter twin, a positron. This pair erupts into existence from nothing. They exist for a fleeting fraction of a second, and then as they have to pay back their energy loan, they find each other, annihilate, and vanish back into the nothingness they came from. This isn't rare. It's happening constantly, everywhere. In the space between your eyes and this screen. In the deepest voids between galaxies. In our perfectly empty box. The seemingly tranquil vacuum is, at its most fundamental level, a seething, chaotic soup of these virtual particles, flashing in and out of existence. The physicist John Wheeler called it quantum foam. Empty space isn't empty. It's a riotous ghost party of phantoms appearing and disappearing too fast for us to see. True nothingness is impossible, because the laws of quantum mechanics will always fill the void with this ghostly, energetic fizz. Proof of the phantoms. The idea of a quantum foam teeming with virtual particles sounds like science fiction. For it to be science, it needs evidence. We can't see virtual particles directly, they exist for way too little time. But we can see their shadows. We can measure the effects they have on the real world. And the most famous confirmation of their existence is called the Casimir effect. Back in 1948, the Dutch physicist Hendrik Casimir came up with a brilliant thought experiment. Imagine taking two perfectly flat, uncharged metal plates and placing them parallel to each other in a vacuum, incredibly close together. Classically, nothing should happen. They should just sit there. But Casimir realized the quantum foam changes everything. Outside the plates, virtual particles of all possible wavelengths can pop into existence. But the tiny space between the plates restricts them. Only waves that fit perfectly into that gap can form there. This means all the longer wavelength virtual particles are excluded from the space between the plates. So you have more virtual particle waves pushing on the outside of the plates than on the inside. This imbalance creates a pressure difference. There's literally more quantum pressure pushing the plates in than pushing them out. The result? The two plates are pushed together by the energy of empty space itself. This isn't just a prediction. This Casimir force has been measured. The experiments are incredibly delicate, but they confirm Casimir's idea with stunning accuracy. Two uncharged plates in a vacuum will attract each other. It's direct, tangible proof that the vacuum isn't empty. It has energy that can exert a real force. The ghosts are real, and they can push things. Another piece of evidence is the Lamb shift. Early quantum theory predicted the precise energy levels of an electron in a hydrogen atom. But when scientists finally measured them with extreme precision in the 1940s, they found a tiny error. The electron's energy was slightly shifted from where the theory said it should be. The reason? The quantum foam. The electron is moving through that seething storm of virtual particles, and it's constantly being jostled and nudged by these fleeting phantoms. This interaction subtly alters the electron's energy just enough to be measured, and the calculated shift perfectly matched the experiment. And the evidence just keeps coming. Recent experiments in 2026 have given us an even clearer picture, detecting how the quantum foam's virtual particles can influence the spin of real particles emerging from high-energy collisions, further confirming that the vacuum is an active, influential environment. This even happens around the most extreme objects in the universe. Black holes. The legendary Stephen Hawking realized that if a pair of virtual particles is created right on the edge of a black hole's event horizon, one might fall in while the other escapes. From our perspective, that escaping particle can't annihilate with its partner anymore. It's been promoted from a virtual particle to a real one. To do that, it has to get energy from somewhere, and it effectively steals it from the black hole. This trickle of escaping particles is called Hawking radiation, and over immense timescales, it causes black holes to evaporate. The fact that black holes can fade away is a direct consequence of the empty space around them being anything but. The grand implications. The quantum foam isn't just a microscopic weirdness. Its existence shapes the entire universe. In fact, everything we see might owe its existence to the ghosts in the void. Let's go back to the very beginning. The Big Bang. In its first tiny fraction of a second, the universe went through an exponential growth spurt called cosmic inflation. A space smaller than an atom swelled to astronomical size in a flash. Now, imagine that tiny, pre-inflation patch of space. It was a quantum realm, filled with the roiling quantum foam. Tiny, random fluctuations were causing minuscule variations in energy from one point to the next. Normally, these average out to nothing. But during inflation, as space itself stretched faster than light, these microscopic quantum fluctuations were stretched with it. Subatomic variations in energy were blown up to cosmological scales. The regions that, by pure chance, had a slightly higher energy density became the gravitational seeds of everything. Over millions and billions of years, these slightly denser regions pulled in more and more matter. They were the kernels around which the first stars and galaxies began to form. The slightly less dense regions became the great voids between galaxy clusters. Think about what that means. The vast, intricate web of galaxies we see in the night sky is basically a macroscopic photograph of quantum fluctuations from the first moment of time. The grandest structures in the universe are fossilized echoes of the quantum foam. Without these ghostly fluctuations, the early universe might have stayed perfectly smooth, and no stars, no galaxies, and no life would have ever formed. The proof is written across the sky, in the temperature maps of the cosmic microwave background, the afterglow of the Big Bang, which perfectly match the predictions for these primordial fluctuations. But this beautiful story comes with a terrifying puzzle. We can calculate the amount of energy this zero-point field should have. And when we do, the number is catastrophically, absurdly large. If all energy curves spacetime, this enormous vacuum energy should have either immediately crushed the universe back into a singularity, or blown it apart so fast that not even an atom could form. But that's not what we see. The universe's expansion is accelerating, but gently. This acceleration is driven by what we call dark energy, which we think is the energy of the vacuum. But when we measure its strength, we find it's about 120 orders of magnitude. That's a 1 with 120 zeros after it's smaller than what our theory predicts. This discrepancy, the cosmological constant problem, is called the worst theoretical prediction in the history of physics. It's the single biggest unsolved mystery in science. Why is the vacuum energy so miraculously and precisely small? It seems some principle we don't understand yet is canceling out almost all of it, leaving just a tiny residue behind. Solving this is the holy grail of modern physics. This brings us to the most profound implication of all. If space is never empty, if it's a dynamic medium fizzing with potential, what does that say about existence? It suggests that the most fundamental state of the universe isn't a static nothingness, but boundless, chaotic activity. Maybe absolute nothing is just an unstable state. Maybe the universe we see is simply what happens when the void can't stand being empty. We started by asking what hides in empty space. And the journey took us from a simple void to a dynamic fabric of spacetime, and then into a seething quantum sea, constantly giving birth to ghostly particles that live and die in the blink of an eye. We found proof of these phantoms in the real forces they exert on our world. We saw how their ghostly fingerprints from the dawn of time are now written across the entire cosmos, forming the blueprint for every galaxy we see today. Ghost in the universe isn't a spook. It's the fundamental energy of space itself, the ceaseless activity that is the baseline of existence. The empty space we perceive is an illusion, a trick of scale. And just beneath that surface is the very engine of creation, the restless heart of the cosmos. It's the ultimate proof that in our universe, there's no escape from reality. There is no off switch. And there is no such thing as absolute nothing. What's left after you delete the universe? What happens when you delete a file from your computer? You drag it to the trash, hit empty, and it's gone. But it isn't, not really. What you've deleted is just the asterisk pointer to that data, a signpost telling your computer that space is now free. The information itself, the ones and zeros that made up your file, often lingers on the hard drive. A ghost in the machine, waiting to be overridden by something new. It's a temporary kind of deletion. A fragile nothingness. But what if we took that idea to its absolute, most terrifying extreme? What if we could bypass the cosmic recycle bin entirely? What if we could delete the entire universe? I don't just mean the planets, the stars, and the galaxies. I mean everything. Every atom in your body. Every speck of dust dancing in a sunbeam. Every single photon of light on its billions of light-years journey. All matter. All energy. If we had the cosmic admin privileges to select all and press delete on reality itself, what would be left? You might think the answer is simple. Nothing. A perfect, absolute, capital N nothing. An empty void. Story over. But the truth is far stranger, far more profound, and it points to a stubbornness at the very core of existence. What's left isn't an empty stage, but the stage itself, along with the rulebook for a play that has no actors. It turns out, the universe refuses to become nothing. And the reason why lies in the one thing that simply cannot be deleted. Stick with me, because what starts as a simple act of cosmic cleanup ends with a revelation that will change how you see the very fabric of reality. Imagine a box. A perfect, theoretical box where we have total control. We start by sucking out every particle of air, every mote of dust, until it holds a vacuum more perfect than anything in the deepest voids of space. For all intents and purposes, it's empty. Now, what if I told you that even after we've stripped away every last speck of matter and every flicker of energy, that box still isn't empty? That something fundamental, something stubborn, is clinging to existence inside those walls, refusing to let true nothingness win. That's the heart of our thought experiment today. We're going on a journey of cosmic deletion, peeling back reality layer by layer to see what remains when there's nothing left. And this isn't just a fantasy. It's a journey into what physicists really mean when they talk about the vacuum, spacetime, and the laws of nature. We're about to see why the most fundamental things in the universe aren't things at all, but the rules that govern it. Setting the rules of the cosmic deletion. Before we start swinging our cosmic delete hammer, we need to set some ground rules. For any thought experiment to make sense, we have to be crystal clear on the parameters. So, what do we mean by delete? In our experiment, delete doesn't mean moving something. We're not shoving all the matter into another dimension or squishing it into a tiny point. We are talking about true ontological erasure. We're causing things to simply cease to exist. Imagine a particle as a line of code in a computer simulation. Deleting it means removing that line. The particle doesn't go anywhere, it's just not in the program anymore. Its existence is terminated. And we need to be systematic. Think of it like a multi-stage cosmic cleanup. We can't just delete everything at once, because the order of operations really matters. The relationship between matter, energy, and the space they occupy is all tangled up. To figure out what's truly fundamental, we have to peel the layers of reality like an onion. Our deletion will happen in 3 phases. First, we'll target asterisk matter. This is the intuitive one. We'll erase every proton, neutron, and electron, every quark and lepton, every atom making up every star, planet, and person. We'll vaporize the tangible universe, leaving behind. Well, that's our first big question. Second, we'll go after asterisk energy and radiation. Once matter is gone, the universe would still be buzzing with fields and forces. So, we'll delete every photon, the particle of light, every gluon, which binds phantom nuclei together. We'll cancel out every gravitational wave, echoes of a cosmos that's no more. And crucially, we'll try to drain the so-called zero-point energy from the vacuum itself, forcing the universe into a state of absolute, impossible cold and darkness. Finally, after all matter and energy are gone, we'll see what, if anything, is left. This is where things get really weird. This is where we come face to face with the foundations of reality itself. We'll be left in a space with no stuff, no energy, no light, no heat. Is this the nothing we've been looking for? Or is there one last, indestructible layer to our cosmic onion? This step-by-step approach is crucial. By removing each component one by one, we can see what depends on what. Does space need matter to exist? Do the laws of physics need particles to act on? Each phase of our deletion is a question we're asking the universe. And each answer will guide us from the familiar world of things to the bizarre, abstract reality that lies underneath it all. So, with the rules in place, let's start the cleanup. First, in the cosmic trash bin. All the matter in the universe. The first layer, deleting all matter. All right, the process begins. First on the chopping block, matter. Look around you. The device you're watching this on, the chair you're in, the air you breathe, your own body, it's all matter. It's the stuff we can touch and see. On a cosmic scale, it's the gas and dust in nebulae, the blazing plasma of stars, the cold rock of planets, and even the mysterious stuff inside black holes. In the language of physics, we're talking about wiping out all baryonic and leptonic matter. Every particle with rest mass is on the list. Let's press the button. Zap. In an instant, it's all gone. Every galaxy vanishes. Every star just stops. Not in an explosion, but by simply ceasing to be. Every planet, asteroid, and molecule of interstellar dust erased. The entire cosmic web, that grand structure of galaxies, dissolves into nothing. The universe is now devoid of things. There are no objects, no structure, no life. So what's left? Your first instinct is probably empty space. A perfect vacuum. A vast, silent, featureless blackness stretching on forever. And for a moment, that feels right. We've created the ultimate void. But this is where our understanding of reality takes a sharp turn. According to our best model of the universe, quantum field theory, this empty space is anything but. It's seething with potential. We didn't just empty the stage, we just cleared it of its most obvious actors. To get this, we need to reboot our idea of a particle. Quantum field theory says the most fundamental building blocks of reality aren't particles at all. They're fields. Imagine the universe is permeated by invisible fields, stretched across reality like an infinite ocean. There's an electron field, a photon field, a quark field, a Higgs field, one for every particle we know. So what's a particle, like an electron? It's not a tiny ball bearing floating in the field. A particle is just a localized vibration, an excitation, a ripple on its field. Think of the electron field as a perfectly calm ocean. If you tap its surface, a ripple appears. That ripple is what we see as an electron. When we deleted all matter, what we really did was smooth out all the ripples on all the quantum fields. And this is the whole point, the ocean itself is still there. The electron field, the quark field, all of them, still exist everywhere, even in their calmest, lowest energy, vacuum state. You can get rid of the waves, but you can't get rid of the ocean. Now, you'd think a calm, zero-energy ocean would be true, nothing. But it can't be. Because of one of the weirdest rules in all of physics, the Heisenberg Uncertainty Principle. Put simply, the principle says you can't know certain pairs of things about a quantum system with perfect accuracy at the same time. This rule also applies to a quantum field's energy. It forbids any field from having a perfectly zero, unchanging energy level. A field that was perfectly flat with exactly zero energy would have a definite energy, zero, and a definite rate of change, zero, which violates the uncertainty principle. Nature forbids perfect stillness. So, what does a quantum field do? It jitters. It constantly fluctuates, even in its lowest energy state. This calm ocean is actually a fizzing, bubbling, chaotic sea of microscopic energy fluctuations. We call this vacuum energy or zero-point energy. And these fluctuations have real consequences. They're constantly borrowing a tiny bit of energy from the vacuum to create pairs of virtual particles. A particle and its antimatter twin that pop into existence for a fraction of a second before annihilating each other and disappearing. Are empty. Vacuum is actually a frantic particle-antiparticle disco, a quantum foam of fleeting existences. This isn't just some wild theory. We have solid proof this is real. One of the most famous examples is the Casimir effect. Predicted in 1948 by Dutch physicist Hendrik Casimir, the effect is this. If you take two perfectly flat, uncharged metal plates and place them incredibly close together in a vacuum, a mysterious force will pull them toward each other. Where does this force come from? It comes from those virtual particles. Outside the plates, virtual particles of all energies can pop into existence. But the tiny gap between the plates restricts which particles can appear, only those whose wavelengths fit neatly into the gap. This means there are fewer virtual particles popping into existence between the plates than outside them. This imbalance in the vacuum's energy creates a real pressure, pushing the plates together. This force has been measured precisely in labs, and it perfectly matches the predictions of quantum theory. The Casimir effect is physical proof that empty space can exert a real force. It's a force from nothing. So, to recap step 1. We've deleted all matter. We've erased the tangible universe. But what's left isn't nothing. It's a universe full of quantum fields, all buzzing with zero-point energy and fizzing with a sea of virtual particles. Our perfect vacuum is a place of unimaginable activity. Now, it's time to escalate. What happens if we try to delete all of this energy, too? The second layer, deleting energy in spacetime. We've successfully erased all matter, but our universe is still buzzing with the simmering energy of quantum fields. So for our next trick, we're pulling the plug on this energy. This is a much more ambitious act of deletion. We're targeting all forms of energy and radiation. That means every photon, the particles of light, is gone. The universe goes totally, utterly dark. We're also deleting any other energy-carrying particles. But we have to go even further. We're now going to do what the laws of physics themselves forbid. We will violate the uncertainty principle and drain every last drop of zero-point energy from the quantum fields. We'll force them into that impossible state of perfect stillness. The quantum foam stops bubbling. The virtual particles halt their frantic dance. The Casimir effect vanishes. We have, by brute force, created a true quantum void. A silent, cold, dark, and energetically dead universe. Surely, this must be nothingness. No matter. No light. No heat. No quantum jitters. We've deleted not just the actors, but the very potential for action. What could possibly be left? The answer is as profound as it is stubborn. Spacetime. Even with nothing in it and no energy bubbling within it, the arena itself remains. The framework of space and the dimension of time, the coordinate system of reality, persists. We tend to think of space and time as just a passive background, a black canvas for reality. But over a century of physics has taught us that spacetime is not a passive backdrop. It's a dynamic, physical thing in its own right. It has structure. It has properties. It is a asterisk something, not a nothing. The first person to really wrestle with this was Isaac Newton, with a brilliant thought experiment known as Newton's bucket. Imagine you're in a totally empty universe. No stars, no galaxies, no reference points. Just you and a bucket of water hanging from a rope. You twist the rope and let the bucket spin. At first, the bucket spins, but the water inside stays still. The water's surface is flat. There's relative motion between the bucket and the water. Then, friction makes the water start to spin with the bucket. Soon, they're spinning at the same speed. There is now no relative motion between the water and the bucket. Yet, something has changed. The water's surface is now concave, curved up the sides by centrifugal force. That's the puzzle. In the first case, there was relative motion, but a flat surface. In the second, there was no relative motion, but a curved surface. What made the water curve? It can't be its motion relative to the bucket. Newton's conclusion was radical. The water wasn't just spinning relative to the bucket. It was accelerating relative to absolute space itself. He argued that space was a real, physical entity, an invisible structure that permeates everything. The curved water was proof it was moving against this absolute background. Even in an empty universe, space itself acts as the ultimate reference frame. Newton was on the right track, but Albert Einstein finished the revolution with general relativity. Einstein showed that space and time are woven together into a single, four-dimensional fabric, spacetime. And this fabric isn't rigid, it's flexible. As the physicist John Wheeler famously said, spacetime tells matter how to move, matter tells spacetime how to curve. Think of the classic analogy: a bowling ball on a trampoline. The flat trampoline is flat spacetime. When you put a heavy bowling ball, a star, on it, the sheet curves. If you then roll a marble, a planet, nearby, it follows the curvature created by the bowling ball. That's gravity. Gravity isn't some mysterious force, it's the geometry of spacetime. Now, back to our experiment. We've deleted all the matter, removed all the bowling balls. You'd think the spacetime trampoline would just snap back flat. And it would, eventually. But the information about that curve doesn't just disappear. When we deleted that star, the dent it made in spacetime would ripple outwards like a wave on a pond. These are gravitational waves, literal ripples in the fabric of spacetime, traveling at the speed of light. So even in our empty, energy-less universe, these ghosts of past events could still be traversing the void. Spacetime itself can carry energy and information in its very shape. An empty but curved spacetime is not nothing. But let's take it one step further. Let's say we wait forever for those ripples to fade, or we just use our god-like powers to smooth the fabric out, making it perfectly flat. No matter, no energy, and now, no curvature. A perfect, flat, four-dimensional grid. This is it. This has to be it. The ultimate void. A blank slate. Is it? Is this finally absolute nothingness? Incredibly, the answer is still no. Because even in this perfectly sterile, flat void, something else remains. Something more fundamental than matter, energy, or even the shape of space itself. The last, most stubborn remnant of reality. The laws of physics. The final remnant. The laws of physics. Let's take stock. We've deleted every particle. We've drained every drop of energy, silencing the quantum foam. We've even flattened the very fabric of spacetime. We're left with what looks like the most perfect void imaginable. A four-dimensional geometric grid, totally inert and empty. And yet, it's not nothing. Because this void is not lawless. It's still governed by a set of rules. The most fundamental things in the universe were never the asterisk things in the universe. They're the rules that dictated the behavior of those things all along. What's left after you delete everything is the universe's operating system. Think about it. Why did quantum fields fizz with energy? Because the Heisenberg Uncertainty Principle demanded it. That principle isn't a particle or a field, it's a rule. A fundamental law of nature. Even though we artificially shut it off, the law itself hasn't gone anywhere. If a new particle appeared, it would instantly be forced to obey. The rule is still there, waiting. Why did matter curve spacetime? Because the equations of general relativity dictated that relationship. Those equations are the rulebook for gravity. They describe how energy would warp spacetime if it were present. We've removed the energy, but the instruction manual remains. It's like having the rules of chess even when you have no board and no pieces. The rules still exist as a concept. What about the speed of light? The constant, c*, is one of our universe's most fundamental settings. It's the maximum speed for information. In our empty void, nothing is moving, but the speed limit is still in effect. It's a property of the vacuum itself. If a photon were to pop into existence, it wouldn't travel at some random speed. It would be instantly constrained to travel at exactly 458 meters per second, because the law is already in place. These laws and constants, the strength of gravity, g, the Planck constant, h, the charge of an electron, aren't physical objects. They are the abstract, mathematical parameters that define the character of our universe. They're the source code of reality. You can delete all the data and files from a program, but the underlying code that defines the program's logic still exists. The laws of physics are the source code of reality. And this isn't just philosophy. We have evidence that these laws are an active part of the vacuum. Let's go back to the Casimir effect. We saw the force is generated by an imbalance of vacuum fluctuations. But why is there an imbalance? Because the laws of electromagnetism dictate how waves must behave between two conductive plates. The rules force certain wavelengths to be excluded, which creates the pressure. The force is a direct result of the laws of physics acting on the vacuum. So what are these laws? They're principles of conservation, like the law of conservation of energy. Energy can't be created or destroyed. They are principles of action, like the law of inertia. An object's motion won't change without a force. They're the rules of interaction, like how electric charges attract or repel. These laws aren't just descriptive, they're prescriptive. They don't just describe what particles happen to do. They dictate what they must do. They constrain reality. Even in our ultimate void, those constraints are present. This empty space is a place where momentum would be conserved, where causality would be limited by the speed of light, and where charges would interact in a specific way. This leads us to the most mind-bending question of all. Are the laws of physics in the universe, or are they the universe? If you strip away everything physical and are still left with a set of mathematical rules, it strongly suggests that the universe is, at its core, mathematical. That reality might not be a collection of things, but a collection of information and relationships, all governed by a logical structure. The nothing we've been looking for seems impossible. We can't get there. Absolute nothingness, a state with no properties, no dimensions, no laws, might just be a logically incoherent idea. The moment you have a void, you have something with the property of being a void. The moment you have a space, it has dimensions. And the moment it exists, it seems to come with a built-in instruction manual. The void stares back, and it does so with rules. So, after our epic cosmic deletion, we are left with the most resilient and fundamental aspect of reality. A set of abstract, invisible, and unbreakable rules. We are left with the logic of existence itself. The universe, it seems, isn't just what's written on the page, but the very grammar that allows anything to be written at all. So where does this journey into the void leave us? We went on a quest for absolute nothingness, peeling back the layers of reality one by one. We erased all matter, the substance of stars and ourselves. But we found that the vacuum wasn't empty. It was a seething ocean of quantum fields. We then deleted all energy, silencing the quantum foam to create a perfect void. But we found the very stage of reality, the fabric of spacetime, refused to disappear. Finally, we even smoothed out spacetime itself. And there, in the deepest layer of reality, we found the last, indestructible remnant. The laws of physics. The rulebook. The operating system of the cosmos. Our attempt to create nothing failed. It failed because the universe seems to have a non-negotiable, foundational structure. The rules aren't written asterisk on the stuff. The rules are the most fundamental stuff there is. This journey forces us to wonder. Is our universe fundamentally made not of particles or energy, but of information? Is reality, at its heart, a mathematical structure? What does it mean if the laws of nature are reality itself? It suggests the line between the physical and the abstract is far blurrier than we ever imagined. The fact that anything exists at all seems to be tied to the fact that there are rules that allow for existence. The void, it turns out, is not a state of nothingness, but a state of pure potential, governed by an eternal and unchanging logic. But pondering whether reality is fundamentally math, or what came before the laws of physics. Well, that's a story for another What If. If you enjoyed this journey to the edge of nothing and back, make sure to subscribe and ring that bell so you don't miss our next exploration. We tackle questions like this every week. And now we want to hear from you. Let us know in the comments. What cosmic, what if, should we tackle next? What mind-bending scenario keeps you up at night? Science just confirmed nothing is actually something. What if the emptiest void in the universe is actually a raging, chaotic storm? What if nothing is impossible? It sounds like a riddle, but it might be one of the most fundamental rules of reality. For centuries, we've imagined a perfect emptiness. We've chased it, tried to build it, and assumed it was just the default state of things. But science has revealed that our universe has a deep, built-in opposition to nothingness. Today, we're going on a journey to the absolute edge of reality to see why true silence and absolute nothing can never, ever exist. The classical quest for the void. Our story starts with a simple idea. Nothing. For most of history, nothing was just the absence of something. Take all the furniture out of a room, it's empty. Take the air out, it's even emptier. This quest for perfect emptiness has been a long-standing goal in science. It all started back in the 17th century with Evangelista Torricelli, a student of Galileo. By inverting a tube of mercury into a dish, he made a space at the top with no air, the Torricellian vacuum. It was a huge deal. For the first time, we had created a pocket of what looked like true nothingness. This quest went on for centuries. We built better and better vacuum pumps, creating chambers with fewer and fewer particles. Today, we can make ultra-high vacuums that are millions of times less dense than the space where our satellites orbit. Inside, we can get down to just a few thousand atoms per cc. It's an unbelievably empty space, where a single atom might travel for miles before hitting another one. But scientists realized removing particles wasn't enough. There was something else to deal with: energy. Emptiness should be cold and still. The stillness part is everything. Temperature is really just a measure of how much particles are moving. The faster they jiggle, the hotter it is. To get true stillness, we need to reach the coldest possible temperature in the universe. Absolute zero. That's 0 Kelvin, or minus 273.15 degrees Celsius. At that temperature, all classical motion should just stop. So, the plan seems simple enough, in theory. To make a patch of perfect nothing, you build a box. You pump out every single particle. You shield it from all light and radiation. And you cool it down to absolute zero to kill all motion. You'd be left with a piece of space with no matter, no light, no energy, no activity. A perfect, silent void. This was the classical dream of nothing. But as we got better at measuring the world, we found out the universe had other plans. At the smallest scales, the very idea of an empty, quiet space completely falls apart. The universe, it turns out, refuses to be still. The first cracks in emptiness. The atomic void. The first clue that something is wrong with our idea of solid doesn't even require leaving our familiar world. You just have to look closer. Pick any solid object near you: a table, a rock, your own hand. It feels solid, dense, continuous. It feels like something. But this is one of nature's greatest illusions. Let's zoom in. Way in. Past the surface, past the cells, down to the building blocks of matter. Atoms. What's an atom made of? At the center is a tiny, dense nucleus. Orbiting that nucleus, at a huge distance, are electrons. And this is where our common sense idea of solid starts to crumble. The scale is just mind-boggling. If you blew up an atom so its nucleus was the size of a marble in the middle of a giant sports stadium, the electrons would be like tiny specks of dust whipping around the very top rows. So what fills that immense space between the marble nucleus and the dust speck electrons? Nothing. An atomic scale vacuum. The chair you're sitting on right now? Your own body? It's over 99,999% empty space. That feeling of solidity you get isn't from touching a continuous surface. It's the electromagnetic force pushing back. The electrons in your atoms are repelling the electrons in the object's atoms. You aren't really touching it. You're floating just above it on a cushion of pure force. This is a pretty wild thought. The something that makes up our world is almost entirely nothing. This was a huge crack in our old understanding of emptiness. The void wasn't just out there, in deep space. It was right here, inside every single thing, inside us. It's the very structure of matter. But this just makes the mystery deeper. If the universe is mostly empty space, what is that empty space? If we could somehow probe the vacuum between a nucleus and its electron, what would we find? For a long time, the answer was assumed to be, well, nothing. A featureless void. A passive stage for particles to act on. But what if we go even smaller? What if we could look at the fabric of that emptiness itself? This is the point where our picture of reality had to completely change. This is where scientists found out that the void isn't vacant. The nothing is not nothing. This is where we run into the quantum realm. The quantum leap. Where things get strange. This is the pivot point. This is where we leave the comfortable world of classical physics and jump into the bizarre, counterintuitive, and amazing world of quantum mechanics. All our ideas about emptiness and stillness are about to get wrecked. This is where things get really weird. The mistake we've been making is thinking of the universe as a big, empty box with little bits of stuff floating in it. Quantum field theory tells us that's completely wrong. The universe isn't an empty container. Instead, the most fundamental thing we know of is a set of interwoven, all-powerful energy fields. Imagine the entire universe is filled with an invisible ocean. Now, imagine there isn't just one ocean, but a whole bunch of them, all layered on top of each other in the same space. There's an electromagnetic field, a Higgs field, and fields for every single particle we know. These fields aren't in space. In a very real way, they're space. They're the fundamental fabric of reality. So what are particles, like electrons and photons? They aren't tiny little balls. They're just ripples or vibrations in their respective fields. A particle is just a concentrated bit of energy, like a wave cresting on the surface of that universal ocean. When you see light, you're seeing ripples in the electromagnetic field. When an electron is detected, you're seeing a little vibration in the electron field. This idea totally changes what a vacuum is. Empty space just means calming the fields down. You can remove the ripples. You can get rid of all the electrons, photons, and quarks. But you can't get rid of the fields themselves. You can smooth out the ocean's surface, but you can't remove the ocean. The fields are always there, everywhere. So even in a perfect vacuum, a place with no matter at all, these quantum fields are still there. You might think, okay, but if they're perfectly calm and still, for all practical purposes, isn't that still nothing? A perfectly flat, motionless ocean isn't doing anything. And that would be a perfectly logical thought. Except for one small, universe-defining problem. The universe has a rule. A strange, unbreakable law that says these fields can never be perfectly calm. A rule that forces them to jitter and churn with a constant, underlying energy. This is the law that makes true nothingness impossible. The cosmic jitter. Heisenberg's uncertainty principle. At the heart of all this is one powerful quantum rule. The Heisenberg Uncertainty Principle. First figured out by Werner Heisenberg in 1927, this principle isn't about our tools being clumsy. It's a fundamental, built-in feature of the universe. The famous version says you can't know the exact position and the exact momentum of a particle at the same time. The more you know one, the less you know the other. Reality itself is just inherently fuzzy. But there's another version of this principle that deals with energy and time. It says you can't know the exact energy of a system in a short moment of time with perfect certainty. And the shorter the time you look, the asterisk more uncertain the energy becomes. This leads to one of the most mind-bending ideas in physics. The universe seems to have a cosmic loophole in the law of conservation of energy. For an impossibly brief moment, a tiny bit of energy can be borrowed from the future, as long as it's paid back almost instantly. The shorter the loan, the more energy you can borrow. This isn't just a math trick. It's happening constantly, everywhere, in every speck of space. Every quantum field, even in a total vacuum, has to follow this rule. They're not allowed to have a perfectly defined energy of zero. Their energy is always fluctuating, bubbling with a baseline hum of activity. This built-in, rock-bottom energy of a system is called its zero-point energy. It's the absolute minimum energy a quantum system can have. Even if you cooled something down to absolute zero, where all classical motion should stop, it would still have this zero-point energy, causing it to jiggle and vibrate. This isn't heat. It's a fundamental property of the quantum world. So, the dream of a perfectly still, silent void is impossible. The uncertainty principle guarantees that even the emptiest vacuum, cooled to the coldest temperature possible, is not truly at zero energy. The fundamental fields that make up that vacuum are forced to perpetually jitter. They hum with a low-level, irreducible energy that can never be turned off. This is the engine that drives the chaos in the void, Meet the quantum foam, the storm in the void. So what happens when a quantum field borrows a little bit of energy from nothing? The answer is as strange as it is awesome. Something is created. The borrowed energy pops into existence as particles. This is the birth of the quantum foam, an idea first dreamed up by physicist John Wheeler. He described the vacuum not as a smooth, empty space, but as a seething and bubbling cauldron. At the tiniest scales of space and time, the vacuum is a chaotic storm of particles popping into existence and then vanishing again. These are called virtual particles. They often burst into existence in pairs, a particle and its antiparticle, like an electron and a positron. They flash into being, borrowing their energy from the vacuum's zero-point fluctuations as allowed by the uncertainty principle. But they're living on borrowed time. To repay their energy debt so that energy is conserved overall, they must annihilate, disappearing back into the nothing they came from. And this all happens on a timescale that is almost too fast to imagine. While they are often created in pairs, the uncertainty principle allows individual virtual particles to pop into existence for fleeting moments as well. Imagine the foam on a freshly poured soda. The surface is a chaotic mess of bubbles appearing and vanishing in an instant. That's a great way to think about the quantum vacuum. It's not empty. It's filled with a constant flux of creation and destruction, a shimmering reality of virtual particles blinking in and out of being. This is the raging, chaotic storm we talked about at the start. The emptiest void you can imagine is, at its most fundamental level, the busiest place in the universe. It's a violent dance of matter and antimatter, a constant reminder that the universe's default state isn't emptiness, but endless activity. For a long time, this was just a theory. How could you ever prove something so fleeting? It seemed impossible. And yet, we have. Seeing the invisible, proof of the void's power. The idea of a vacuum teeming with ghostly particles sounds more like sci-fi than hard science. But physicists have come up with some brilliant ways to prove that this quantum foam is real. We've seen the effects of the void, and we've measured its power. The most famous proof is the Casimir effect. Predicted by Dutch physicist Hendrik Casimir in 1948, the experiment is beautifully simple. Imagine you take two perfectly flat, uncharged metal plates and place them incredibly close to each other in a vacuum. Classically, you'd expect nothing to happen. But remember the quantum foam. The vacuum is filled with virtual particles of all possible wavelengths popping in and out of existence everywhere outside the plates, and in the tiny gap between them. But the gap between the plates acts like a filter. Only virtual particles with wavelengths that can fit into that gap can exist there. This means there are more virtual particles pushing on the asterisk outside of the plates than on the asterisk inside. This imbalance creates a tiny, but real, pressure pushing the plates together. This Casimir force was incredibly difficult to measure, but a landmark experiment in 1996 was part of a decades-long effort that has now confirmed it with high precision. The nothing of the vacuum was creating a real, physical force. Another key proof is the Lamb shift. In the 1940s, Willis Lamb found a tiny, unexpected difference in the energy levels of the hydrogen atom. Existing theories said two specific electron orbitals should have the exact same energy, but they didn't. The explanation was that the electron, as it orbits the nucleus, is constantly being jostled by the virtual particles of the vacuum. This endless buffeting from the quantum foam slightly changes the electron's energy. And the proof just keeps coming. As recently as February 2026, new experiments have made the reality of the quantum foam clearer than ever. At Columbia University, researchers showed that these vacuum fluctuations can have real, tangible effects on materials. They found that by placing one material close to a superconductor, the quantum vacuum fluctuations were enough to actually shut down the superconductivity. As one of the lead scientists, Professor Angel Rubio, put it, we now have experimental proof of vacuum-mediated interactions in a material system. Around the same time, scientists at Brookhaven National Laboratory found a way to essentially catch virtual particles in the act. By smashing protons together in the relativistic heavy ion collider, they gave a burst of energy to the virtual particles in the vacuum, kicking them up into real, detectable particles. It was, as physicist Zhou Dunming II described, a unique window into the quantum vacuum. Even black holes provide evidence. Stephen Hawking predicted that if a pair of virtual particles is created at the edge of a black hole's event horizon, one might fall in while the other escapes. To an outside observer, it looks like the black hole itself is emitting radiation. This Hawking radiation is a direct result of vacuum fluctuations. From the force between two plates to the energy of an atom and the slow evaporation of black holes, the evidence is overwhelming. The storm in the void is real. The cosmic architect, nothing's role in everything. This quantum foam isn't just a weird, microscopic side effect. The endless storm in the void is actually one of the most important architects of our entire universe. To see how, we have to go back to the first moments after the Big Bang. The universe was incredibly hot, dense, and expanding at an insane rate in a process called cosmic inflation. In this early state, the universe was almost perfectly uniform. But almost is the key word. The quantum foam was still there, causing tiny, random fluctuations in the energy density of the infant universe. Normally, these fluctuations just average out to nothing. But during the hyper-fast expansion of inflation, something amazing happened. These microscopic ripples were stretched to colossal, astronomical sizes. A quantum fluctuation smaller than a proton was suddenly magnified to be larger than a galaxy. Those tiny, random energy variations became the seeds of cosmic structure. The regions that, just by chance, had slightly more energy had slightly more gravity. Over millions of years, these denser spots started pulling in more and more matter. Gas and dust gathered, stars lit up, and eventually, these seeds grew into the vast galaxies and clusters of galaxies we see today. The slightly less dense regions became the great voids between them. Think about that. Every galaxy, every star, every planet including ours owes its existence to a random hiccup in the nothingness of the early universe. The grand structure of the cosmos is a fossilized record of the quantum foam. And the story might not even end there. The energy of the void could also be deciding the ultimate fate of our universe. Astronomers have found that the expansion of the universe isn't slowing down, it's accelerating. Something is pushing everything apart. Scientists call this mysterious force dark energy. One of the main suspects for dark energy is the vacuum energy itself, that collective zero-point energy of all the quantum fields. The problem, often called the cosmological constant problem, and one of the biggest headaches in physics, is that when scientists try to calculate how much vacuum energy there should be, they get a number that is absurdly, comically larger than what we observe by a factor of 10 to the power of 120. Still, the idea is powerful. The same quantum jitter that seeded the galaxies may now be driving the universe's accelerating expansion. The final frontier. Can the laws themselves vanish? We've stripped away matter, radiation, and even motion, only to find an unquenchable fire of quantum activity. But this brings up a deeper, more philosophical question. What if we could go further? What if we could remove not just the stuff in the universe, but the rules that run it? If we could erase the laws of physics, would we finally get to absolute nothing? This is the ultimate thought experiment, where physics starts to bleed into philosophy. Imagine a cosmic switch that turns off gravity, electromagnetism, and the quantum uncertainty principle. Poof! No more rules. Are we finally left with a true, absolute void? This is where we hit a logical paradox. The laws of physics aren't like traffic laws written for pre-existing roads. The laws are the roads. Think about gravity. Einstein showed us that spacetime isn't a passive background, it's a dynamic thing. As physicist John Wheeler famously said, spacetime tells matter how to move. Matter tells spacetime how to curve. The law of gravity is just the description of how the fabric of spacetime behaves. So what happens if you erase that law? You don't get a flat, empty spacetime. You get no spacetime at all. The very concept of space, of distance, of a place where nothing could exist, is defined by the laws you just tried to erase. Removing the rules removes the entire arena. It's a logical contradiction. To say, absolute nothing exists, you need a context for that nothing to be in. You need a state that has the property of being nothing. But properties and states are all defined by physical laws. Without them, you don't get emptiness, you get an incoherent mess. It's like trying to imagine a story with no language or grammar. It isn't an empty story, it's not a story at all. Physics shows us that emptiness is not a stable state. Nature seems to hate a perfect void so much that it's a logical impossibility. Existence isn't an accident. It seems to be the only option. If this trip into the quantum void blew your mind, consider subscribing so you don't miss our next exploration of the cosmos. Your curiosity is what makes these deep dives possible. We started with a simple question. What is nothing? We imagined an empty box, a silent void. We journeyed down, past the atoms that are mostly empty space, and into the very fabric of that emptiness. And there, we found not a quiet void, but a raging storm. We found a fundamental rule, the Heisenberg Uncertainty Principle, that forbids true stillness and forces the universe to hum with energy. We met the quantum foam, a sea of virtual particles, and saw proof of its power in the forces it creates and the very particles it can become. We saw how the grand design of the cosmos was born from its random jitters. And finally, we hit the ultimate wall. The logical impossibility of erasing the laws that define existence. The universe, it seems, is built on a foundation of activity. Its default state is not emptiness, but endless, creative potential. Nothingness isn't the baseline that something came from. Instead, it seems nothingness is a fundamentally unstable, and maybe even illogical, idea. So, the next time you look up at the dark emptiness between the stars, remember what you now know. You're not looking at nothing. You're looking at the engine of creation. A chaotic, powerful storm that stretches across the cosmos, a constant reminder that in our universe, existence is the only option. And the deepest silence is screaming with potential. Science just proved nothing is impossible. Have you ever really stopped to wonder what nothing actually means? It's a word we toss around every day. There's nothing in the box, or I have nothing to do. We think of it as simple emptiness, a void. But what if I told you that in the entire, vast history of the cosmos, true, absolute nothing has never existed? What if the universe has a fundamental, unbreakable rule? Emptiness is forbidden. This isn't a riddle or a philosophical game. It's a conclusion physics has been forced to accept, a truth proven by experiment. It turns out the very fabric of reality hates a vacuum in the most profound way imaginable. The default state of our universe isn't a silent, empty void waiting for something to happen. The default state is something. A constant, seething, bubbling cauldron of potential, where reality is being written and rewritten trillions of times a second, in every corner of space. So, get ready to question what you see with your own eyes. Today, we're journeying to the absolute bottom of reality, to a place where common sense completely breaks down. We're going to unravel a cosmic riddle and discover why science has proven that a state of absolute nothing is the one thing that is truly impossible. hold your hands up, about a foot apart. The space between them looks like nothing, right? Just air. But now, imagine we could pump all that air out. Every last atom, every stray particle, until we have a perfect vacuum. The perfect picture of emptiness. But what if I told you that in that tiny gap, a drama of creation and annihilation is unfolding trillions of times per second? Physicists have discovered the universe has a non-negotiable rule. True emptiness is forbidden. This isn't just a theory, it's a proven fact. And it means the default state of reality isn't nothing. It's a constant, bubbling cauldron of something. The grand illusion of emptiness. For most of human history, nothing was, well, simple. It was just the absence of something. The ancient Greek philosophers debated it endlessly. Aristotle famously argued that nature abhors a vacuum, a concept he called horror vacui. He believed any void would be instantly filled because, to him, nothingness was a logical paradox. How can nothing be anything? This idea feels right. An empty cup isn't really empty, it's full of air. Pump the air out, and you get a vacuum. For centuries, this was our best shot at emptiness, a space devoid of matter. We looked at the vast, dark stretches between the stars and saw the ultimate nothing. A silent, static stage for the cosmic drama. This picture is clean, simple, and completely wrong. The first crack in this idea didn't come from astronomy, but from a force we've all played with: magnetism. Take a bar magnet and sprinkle some iron filings on a piece of paper above it. There's nothing visibly connecting the magnet to the filings. The space looks empty. And yet, the filings leap into elegant, ordered lines, tracing arcs from one pole to the other. What are they tracing? They're revealing an invisible structure filling the empty space. They're tracing the lines of a magnetic field. This revolutionary idea, pioneered by the 19th century scientist Michael Faraday, changed everything. He imagined that space itself was filled with these invisible fields of influence. The magnet wasn't reaching out and grabbing the filings. It was creating a disturbance in a field that was already there, and the filings were just responding. This was a huge shift. Suddenly, empty space wasn't so empty. It was filled with invisible, influential forces. You can't see a magnetic field, you can't touch it, but its presence is undeniable. The same is true for an electric field. And, as Einstein later showed with general relativity, the biggest field of all is spacetime itself, a dynamic fabric that can be warped and curved by mass and energy, creating the force we feel as gravity. This field perspective was the first nail in the coffin for the idea of true nothingness. It taught us that space wasn't a passive, empty box. It was an active medium, humming with forces and potentials. But even Faraday and Einstein couldn't have imagined where this idea would lead. As early 20th century physicists probed the tiniest bits of reality, they hit a wall. The old model of particles as tiny billiard balls just didn't work. Particles acted like waves. They could be in multiple places at once. They could appear and disappear. To understand reality, physics needed a new foundation. It had to let go of tangible objects and embrace something far stranger: the universal blueprint of quantum fields. This was the moment the last illusion of nothing began to dissolve forever. The universal blueprint, quantum fields. To get what comes next, you have to reboot your entire idea of the universe. Let go of the picture of a big, empty box containing things like electrons and photons. The shocking truth revealed by our most successful theory ever, quantum field theory, is this: the universe is the things. There is no box. There are only the fields. Imagine the universe not as a stage, but as an infinite, restless ocean. This ocean is the fundamental reality. Now, what we call a particle, say, an electron, isn't a tiny boat floating on the ocean. An electron is just a ripple, a localized vibration, a tiny excitation of the ocean itself. This is the heart of quantum field theory, or QFT. It says the most fundamental things are not particles, but fields. There's an electron field that permeates every point in spacetime. There's a photon field, quark fields, a Higgs field, one for every fundamental particle, all layered on top of each other, all coexisting everywhere. Let's go back to that ocean. When it's perfectly calm and flat, in its lowest energy state, we could call that the vacuum. It looks like nothing is there. But the ocean itself, the water, is still there, just resting. Now, if you dip your finger in, you create a ripple. That ripple is a packet of energy that travels across the water. That ripple is, for all intents and purposes, a particle. If you add enough energy, say, by slapping the water, you create a big splash of many ripples. You've just created particles. When the ripples die down, the particles have been annihilated. This is exactly what QFT tells us is happening. An electron is just a quantum of excitation in the electron field. A photon is a quantum of excitation in the electromagnetic field. When a particle accelerator smashes two particles together, that immense energy is dumped into the quantum fields, causing them to ripple violently. We detect those ripples as a shower of new particles. This beautifully explains how particles can be created and destroyed. They aren't solid things, just temporary manifestations of energy in their underlying fields. So, what does this mean for nothing? A perfect vacuum isn't the absence of everything. A vacuum is simply the state where all the quantum fields are in their lowest possible energy state. It's the calm ocean. The fields themselves, however, the very potential for existence, are still there, woven into the fabric of spacetime. They can never be removed. They are the fabric of spacetime. This is a profound shift. Even in the most perfect vacuum imaginable, the machinery of reality remains. But the story gets even weirder. Because it turns out these fields are never truly at rest. The calm ocean is an illusion. The restless void, vacuum energy and virtual particles. So, a vacuum is just the ground state of all the quantum fields. But what does ground state mean in the bizarre world of quantum mechanics? Here, we run into one of science's most famous rules, a principle that injects a fundamental restlessness into reality. Heisenberg's Uncertainty Principle. In its most common form, it says you can't know a particle's exact position and momentum at the same time. But there's another version, the energy-time uncertainty principle. It states that you cannot know the exact energy of a system for a very short interval of time. Think of it this way. The energy of a quantum field is like the surface of a pond. The uncertainty principle says you're not allowed to have a perfectly flat, glassy surface for any length of time. If you look at it for an almost infinitesimally brief snapshot, the surface can be incredibly choppy. Over a longer period, it averages out to look calm, but in those fleeting moments, all hell can break loose. The energy-time uncertainty principle. Delta E times delta T is greater than or equal to h2. Means that for a tiny fraction of a second, the energy in a patch of empty space can fluctuate wildly. The vacuum is allowed to borrow energy from nothing, as long as it pays back the debt almost instantly. And what happens when the vacuum borrows energy? That energy manifests as ripples in the quantum fields. And what are ripples in quantum fields? Particles. This is the origin of so-called virtual particles. All across the universe, in every cubic nanometer of the most perfect vacuum, a frantic dance is taking place. An electron and its antimatter twin, a positron, spontaneously emerge from the void, fly apart, and then, an instant later, slam back into each other and disappear. This isn't rare. It's happening constantly, everywhere. The empty Vacuum is actually a seething, bubbling cauldron of these virtual particle pairs. Physicists call this chaotic landscape quantum foam, a name coined by the physicist John Wheeler. He imagined spacetime at the smallest possible scales not as a smooth sheet, but as a foamy, jittery sea of possibilities. Now, it's totally reasonable to think this sounds like a mathematical fantasy. How could we possibly know this invisible world of fleeting particles is real? It sounds like magic. But this is where science takes its most powerful step. It doesn't just imagine, it tests. And in one of the most elegant experiments ever devised, physicists found a way to reach into the quantum foam and prove that nothing has tangible, physical power. The undeniable proof. The Casimir effect. The idea of a vacuum teeming with phantom particles was hard to swallow, even for many physicists. How could you prove the existence of something that disappears too quickly to be measured? The answer came from a Dutch physicist named Hendrik Casimir in 1948. He had a startling realization. If this quantum foam was real, it should be exerting a kind of pressure on everything. And he devised a brilliant way to measure it. Here is the experiment he proposed, now known as the Casimir effect. Imagine you take two perfectly flat, uncharged metal plates. You bring them into a perfect vacuum and place them parallel to each other, incredibly close together, just a few micrometers apart. According to the theory, the space outside the plates is filled with a churning sea of virtual particles of all possible wavelengths. But the tiny gap between the plates acts like a resonant cavity. It imposes a physical boundary. Just like a guitar string can only vibrate at specific frequencies, only virtual particles whose wavelengths fit a whole number of times into the gap are allowed to exist there. This means all the long wavelength virtual particles are excluded from the space between the plates. They simply don't fit. This creates an imbalance. There are more virtual particles popping into existence outside the plates, pushing inward, than there are inside, pushing outward. The result? A net pressure from the empty space outside, pushing the two plates together. This Casimir force is unbelievably tiny, but it's real. For decades, it was just a prediction. But technology caught up. In 1997, physicist Stephen Lamoureux conducted a precision measurement that confirmed Casimir's prediction to within about 5% of the theoretical value. Subsequent experiments have refined this measurement to even greater accuracy, leaving no doubt. Let's just appreciate how profound this is. Scientists took two uncharged plates, put them in a vacuum where there is nothing, and watched them get pushed together by a force generated by that very nothing. It's the smoking gun for the reality of the quantum vacuum. It's undeniable proof that empty space is not empty. The vacuum has energy, what we call zero-point energy, and it can do real, measurable work. The case is closed. The vacuum isn't a void, it's a dynamic, energetic plenum. Science has proven that at the most fundamental level, there is no such thing as empty, static nothing. And this fact has staggering implications for the origin and fate of the entire cosmos. If your mind is blown by the fact that empty space is powerful enough to move objects, then hit that subscribe button. Because next, we're going to explore what this restless void means for the biggest question of all. Why is there a universe in the first place? The grand implications. A universe from almost nothing. We've found that the universe forbids true emptiness. The vacuum, once thought to be a void, is actually a seething cauldron of virtual particles and energy. So now we have to face the ultimate question. Why is there something rather than nothing? For most of history, this was a question for philosophy, not science. The existence of the universe was a given. The alternative, absolute nothingness, seemed like the logical, stable default. Why should a universe exist at all? But the discovery of the quantum vacuum flips this ancient question on its head. If a vacuum, the closest thing to nothing, is inherently unstable and boiling with energy, then maybe nothing isn't the default state. Maybe something is. If the laws of physics demand that even the lowest energy state is a hive of activity, then perhaps a state of true, absolute nothing is the one thing that's physically impossible. This has led to one of the most exciting ideas in modern cosmology, championed by physicists like Lawrence Krauss. The idea is that the Big Bang itself could have been a quantum fluctuation. If the universe's total energy is zero with the positive energy of matter balanced by the negative energy of gravity, then the laws of quantum mechanics could allow it to pop into existence from nothing without violating any rules. Now, it's crucial to be precise here. When physicists like Krauss say nothing, they mean a quantum vacuum, a state without space, time, or matter, but still subject to the laws of physics. As critics rightly point out, that's not the same as absolute, philosophical nothingness. But this distinction pushes us even deeper, past physics and into pure logic. Let's try to define absolute nothing, the complete absence of everything. No space, no time, no matter, no energy, and critically no laws or rules. If this state of absolute nothing truly has no properties whatsoever, then it can't have the property of being stable. It can't have any limitations. And if it has no limitations, then there's nothing to forbid something from arising. A state with no rules can't have the rule, nothing can be created. It's a self-defeating paradox. So, whether we approach it from physics or from logic, we arrive at the same staggering conclusion. A state of true, absolute nothingness seems to be the one impossible thing. The default state of reality isn't absence. It is presence. It is potential. It is existence. Let's come back, one last time, to the space between your hands. For your whole life, you've seen it as emptiness, an absence, a passive void. But now you know the truth. That space is not empty. It's the most fertile ground in the universe. It is a physical fabric woven from fundamental fields, humming with the energy of the cosmos. It's a chaotic quantum foam, where particles are born and die in a ceaseless dance. That nothing between your hands is pushing on them with a real, physical force. The discovery that the vacuum is not a void fundamentally reshapes our place in the cosmos. It tells us that the existence of something isn't a strange miracle that needs a special explanation. It is the natural, inevitable, default state of reality. The universe exists because a state of true nothingness is a contradiction in terms. We aren't just observers of this universe. We are a part of its relentless creativity. Every atom in your body is just a persistent ripple, a complex pattern of excitation in these fundamental fields. We are, in the most literal sense, disturbances in the vacuum. We are the universe, waking up and becoming aware of itself. The fact that we can even ponder this question is the ultimate proof. It is the universe's own declaration that nothing is impossible. The deepest truth of reality is not a silent void, but a song of perpetual becoming. The ghost that haunts every vacuum in the universe. What if you could erase the entire universe? Every star, every planet, every single atom. Just gone. You're left with a perfect, absolute vacuum. Utter emptiness. But what if I told you that even in that perfect nothingness, a ghost remains? And I don't mean a metaphor. I mean a real, physical presence that refuses to be silenced. This is the story of the hum of the universe, and why even in the most profound emptiness, there is always something. The classical dream of emptiness. For thousands of years, we've been arguing about nothing. The ancient Greeks were some of the first to really wrestle with it. You had philosophers like Parmenides who argued a true void was impossible, a logical contradiction. I mean, how could nothing exist? Just talking about it gives it a property, which means it can't be truly nothing. But then you had the atomists, like Democritus, who said reality was just tiny particles called atoms zipping through an empty void. For them, nothingness wasn't just possible, it was essential. It was the stage where existence happened. For centuries, the no void camp was winning, mostly thanks to Aristotle. His declaration that nature abhors a vacuum became scientific law. He figured that any motion through a total void would have to be instantaneous because there's no resistance, which just seemed absurd. And that idea stuck for almost 2,000 years. The first real crack in that worldview came in the 17th century. In 1643, a student of Galileo's named Evangelista Torricelli did something revolutionary. He filled a glass tube with mercury, sealed one end, and flipped it upside down in a bowl of more mercury. The column of liquid fell, but it stopped, leaving a space at the top. What was in that space? Torricelli argued it was a vacuum, the first one ever made in a lab. The pressure of the air on the mercury in the bowl was holding up the column. That space above it was, for all intents and purposes, empty. This discovery opened the floodgates. Scientists like Blaise Pascal and Robert Boyle started building vacuum pumps, showing off the incredible power of air pressure and exploring this weird new nothingness. The most dramatic proof was Otto von Guericke's experiment in 1654, where two teams of horses couldn't pull apart two copper hemispheres once the air was pumped out from between them. It seemed settled. The void was real. Space wasn't a substance, it was an absence. But then, the 19th century came along and messed things up again. The discovery that light acts like a wave created a huge problem. Every wave we knew needed something to travel through. Sound needs air, ocean waves need water. So, what was light using to travel from distant stars to us across the vacuum of space? To solve this, physicists brought back an old idea: the luminiferous ether. They imagined it as this invisible, undetectable substance that filled every inch of space, even in a vacuum. It had to be super rigid to support light's incredible speed, but also so flimsy that it didn't slow down the planets. For a while, the ether seemed like a weird but workable solution. The universe wasn't empty, it was filled with this ghost medium. The next step was to prove it existed. The most famous attempt was the Michelson-Morley experiment in 1887. Their plan was brilliant. As the Earth flies through space, it should be moving through this stationary ether, creating an ether wind. This wind ought to make light traveling into it seem slower than light traveling with it. They built an incredibly precise device to measure this difference. They ran their experiment, a masterpiece of engineering, on a stone slab floating in mercury, and they found absolutely nothing. No difference in the speed of light, no matter which way they pointed their machine. They tried again and again, at different times of the year, but the result was always the same. The ether wind just wasn't there. This was a bombshell. It was a massive piece of evidence against the ether and threw physics into chaos. How can light be a wave if it has nothing to wave through? For a brief moment, it seemed like we were back to a truly empty, silent vacuum. But this was just the quiet before a much stranger storm. The death of the ether didn't give us the simple emptiness we expected. It set the stage for a far more radical idea of what nothing really is. The quantum awakening. The turn of the 20th century was a wild time for physics. The old rules were breaking down. The Michelson-Morley experiment was one crack. Another came from studying the light from hot objects, or black body radiation. Classical physics predicted that these objects should spit out an infinite amount of energy, which was so obviously wrong it was nicknamed the ultraviolet catastrophe. In 1900, a physicist named Max Planck tried a desperate fix. He suggested that energy wasn't a smooth, continuous flow, but came in little packets, or quanta. It was a strange idea, almost a mathematical trick. But 5 years later, a young patent clerk named Albert Einstein took it seriously. He used it to explain how light could knock electrons off a metal plate, the photoelectric effect, by proposing that light itself was made of these energy particles, which we now call photons. This was the dawn of quantum mechanics, a new rulebook for the universe on the tiniest scales. And the rules were bizarre. They painted a picture of a world built on probabilities and uncertainty, where particles could also be waves, and just looking at something could change it. The neat, clockwork universe of Isaac Newton was being replaced by a fuzzy, weird, and deeply counterintuitive reality. One of the weirdest and most important new rules was Werner Heisenberg's Uncertainty Principle from 1927. It says there's a hard limit to how well you can know certain pairs of things about a particle at the same time. For instance, the more precisely you know a particle's position, the less precisely you know its momentum, and vice versa. And this isn't because our measuring tools aren't good enough. It's baked into the rules of reality itself. A particle just doesn't have a perfectly definite position and a perfectly definite momentum at the same time. So, what does this mean for a vacuum? A classic vacuum is supposed to be perfectly still, with zero energy. Any particle in it would have a precise position and a precise momentum, zero. But the uncertainty principle says, nope. If a particle had exactly zero momentum, you'd know its momentum perfectly, which means you'd have zero clue where it is. Its position would be infinitely uncertain. Nature just refuses to be pinned down like that. This leads to a wild conclusion. No quantum system can ever have an energy of exactly zero. Even in its lowest possible energy state, it has to keep a tiny, unavoidable jiggle. This minimum energy is called the zero-point energy. The idea was first developed by Max Planck around 1911 and further explored by Einstein and Otto Stern a couple of years later. It's the energy that's left over even at absolute zero, when all heat is gone. It's a fundamental, irremovable feature of the quantum world. And this isn't just about particles. It applies to space itself. The old idea of a passive, empty vacuum was dead. The new quantum vacuum was a seething, buzzing, active place. The uncertainty principle also has a version that connects energy and time. It says you can't be sure of the exact energy of a system for a short period of time. This lets little bursts of energy be borrowed from the vacuum for a split second. This borrowed energy can pop a pair of virtual particles, a particle and its antimatter twin, into existence. They live for a fleeting moment before smashing into each other, annihilating, and paying the energy back. This happens everywhere, all the time. The space you think is empty is actually a roiling foam of these phantom particles. This quantum foam, this sea of endless activity, is the true nature of the vacuum. This is our ghost. It's not that we haven't tried hard enough to get everything out of space. It's that the rules of the universe themselves forbid true emptiness. The vacuum isn't a state of nothing. It's the ground state, the lowest energy level of something. And that something is the quantum field. Weaving the fabric of reality, quantum fields. So, if the vacuum isn't empty, what is it full of? The answer comes from one of the most successful theories in all of science: quantum field theory. To get your head around this, you have to throw out that picture you learned in school of tiny billiard balls called particles bouncing around in empty space. It's not totally wrong, it's just not the whole story. According to quantum field theory, or QFT, the most fundamental things in the universe aren't particles at all. They're fields, invisible, fluid-like substances that stretch across all of space and time. Think about the magnetic field around a magnet. You can't see it, but you can feel it pulling on a paperclip. That's a field. QFT says everything is a field. There's an electron field, a quark field, a photon field, and one for every other fundamental particle. These fields aren't just math, they're the stuff the universe is made of. So, where do particles come from? In QFT, particles are just little, vibrating ripples in their underlying field. Imagine a huge, perfectly calm ocean stretching to the horizon. That calm ocean is a field in its lowest energy state, the vacuum. Now, tap the water. You make a ripple. That ripple travels across the surface, carrying energy. That ripple is a particle. A ripple in the electron field is what we experience as an electron. A ripple in the photon field is what we see as a photon, a particle of light. This is a huge change in perspective. The universe isn't a bunch of things moving around in space. The universe is a collection of these fields. What we call empty space is just all these different fields lying dormant in their lowest energy state. But, as we just learned from the uncertainty principle, that dormant state is never perfectly still. The fields are always quivering. That constant quivering is the zero-point energy. It's the energy of the fields themselves, jiggling because quantum mechanics won't let them be perfectly flat. The virtual particles are just a useful way of picturing the effects of these constant field vibrations. They're like the tiny, fleeting crests on the surface of this deep, universal ocean. This idea elegantly explains why every electron in the universe is identical. It's because they're all just ripples in the same electron field. It also explains how particles can be created and destroyed. If you have enough energy, say, in a particle collider, you can smack a field hard enough to create new, lasting ripples, which we see as new particles. So when we talk about the ghost in the vacuum, we're really talking about the fundamental, non-negotiable energy of these quantum fields. Even if you could scoop out every particle in the universe, the fields themselves would remain. You can't have space without the fields. And because of quantum mechanics, those fields can never be truly quiet. They will always hum with energy. That hum is the zero-point energy. It's the ghost, the persistent whisper that guarantees nothing can ever be truly nothing. The proof in the nothingness. The Casimir effect. Okay, this all sounds wonderfully weird. A universe made of invisible, quivering fields. A vacuum that's secretly seething with energy. But is there any proof? Can we actually see the effects of this ghost? The answer is yes. And the proof is one of the most clever and mind-bending experiments in modern physics. The Casimir effect. Back in 1948, a Dutch physicist named Hendrik Casimir was studying the weak forces that make neutral atoms stick together. While talking it over with Niels Bohr, one of the founders of quantum theory, Bohr casually suggested that maybe it had something to do with the vacuum's zero-point energy. Casimir took that idea and ran with it. He dreamed up a simple scenario. Take two perfectly smooth, uncharged metal plates and place them parallel to each other in a perfect vacuum, incredibly close together. Classically, nothing should happen. They're neutral, so there's no electrical force. There's nothing in the vacuum to push or pull them. They should just sit there. But Casimir realized that if the quantum vacuum is real, if it's a sea of fluctuating fields churning with virtual photons of all possible wavelengths, then the plates would change the vacuum around them. Outside the plates, virtual photons of every wavelength can pop into and out of existence. But between the plates, it's a tight squeeze. Like a guitar string that can only vibrate at certain frequencies, only virtual photons whose wavelengths fit neatly into the tiny gap are allowed to exist there. This means that a lot of the longer wavelength photons that can exist outside are forbidden from appearing between the plates. The end result is that there are fewer possible jitters in the vacuum between the plates than outside them. This imbalance creates a pressure difference. The greater energy of the vacuum outside the plates exerts a tiny but real pressure, pushing the plates together. There is literally less nothing, between the plates than outside of them, and this difference creates a force. We now call this the Casimir force. Casimir calculated the exact strength of this force and found it would be incredibly weak, but would get stronger very quickly as the plates got closer. For plates just a micron apart, about 1/100th the width of a human hair, the pressure is tiny, just a few millionths of the air pressure we feel every day. For nearly 50 years, this was just a theory. The force was so faint that measuring it with precision was beyond our reach. But in 1997, a physicist named Stephen Lamoureux finally did it. Using an ingenious device, he measured the tiny attraction between a sphere and a plate. The results were stunning. The measured force matched Casimir's prediction to within 5%. The experiment has been repeated many times since with even greater accuracy, proving the force is real. The vacuum is not a passive void. It has a structure that can be changed, and those changes have real, physical consequences. Those two metal plates are being pushed together by the ghost in the machine, by the pressure of the universe's constant quantum hum. It's tangible proof that even in the purest emptiness we can imagine, there is always something. The architect of the cosmos. The Casimir effect is amazing proof that the vacuum isn't empty. But the impact of this buzzing, energetic nothingness goes way beyond just pushing two plates together. This ghost might be the architect of the entire universe. Let's start big. In 1998, astronomers studying distant supernovae found something that completely changed cosmology. They discovered that the universe isn't just expanding, but that the expansion is speeding up. Some mysterious, invisible influence is pushing everything apart, overwhelming gravity. They gave this mystery a name: dark energy. Our best measurements today suggest that dark energy makes up about 68% of everything in the universe. It's the dominant force in the cosmos, and we have almost no idea what it is. But the leading suspect is the energy of the vacuum itself. The idea is that this zero-point energy that fills all of space has a natural, repulsive effect. It's a kind of anti-gravity that causes space itself to expand. This idea actually goes all the way back to Einstein. When he was first developing general relativity, his equations showed the universe should be either expanding or contracting. He thought the universe was static, so he added a fudge factor to his equations to hold gravity back, which he called the cosmological constant. When it was later discovered the universe was expanding, Einstein supposedly called this his biggest blunder. But now, with the discovery of the accelerating expansion, his blunder is back with a vengeance. The cosmological constant is the simplest way to describe a constant energy density built into space itself, in other words, vacuum energy. There's just one tiny problem. Actually, it's a gigantic problem, maybe the worst theoretical prediction in the history of physics. When physicists use quantum field theory to calculate how much zero-point energy should be in the vacuum, the number they get is catastrophically, comically huge. It's about 120 orders of magnitude. That's a 1 followed by 120 zeros bigger than the value we actually observe. If the vacuum energy were really that high, the universe would have blown itself apart so fast that stars, galaxies, and even atoms never could have formed. This massive disagreement is called the cosmological constant problem, and it's one of the biggest mysteries in science. It tells us we're missing something huge about how quantum mechanics and gravity work together. But the fact that a tiny bit of this energy does seem to exist and is pushing our universe apart shows what a central role this ghost plays in the cosmos. And the vacuum's influence isn't just on the grandest scales. It's also critical for our very existence. The standard model of particle physics is built on quantum fields. The Higgs field, for instance, permeates all of space. Particles like electrons and quarks get their mass by moving through it, like dragging a spoon through molasses. The Higgs boson, discovered in 2012, is just a ripple in this field. Without the Higgs field having a non-zero energy in the vacuum, all particles would be massless, zipping around at the speed of light. The stable, complex stuff we call matter could never exist. From giving mass to particles to driving the expansion of the cosmos, the energy of the void is everywhere. It's not some subtle footnote. It's the invisible scaffolding and engine of creation. The ghost in the vacuum isn't some quiet phantom on the sidelines. It's the architect and driving force of everything we know. We started this journey with a simple idea. A perfect void, absolute nothingness. We imagined wiping the slate clean, every star, every particle, gone. But at every step, reality has surprised us. The deeper we peer into the heart of nothing, the more something we find. The old dream of a silent, passive void was shattered by the weird rules of quantum mechanics. We learned that the universe, at its most basic level, isn't made of little things, but of vast, unending fields woven into space and time itself. The uncertainty principle guarantees these fields can never be truly still. They must always hum with a minimum energy, the zero-point energy. This quantum restlessness fills the vacuum with a ghostly dance of virtual particles, a reality proven by the Casimir effect, where mirrors are pushed together by the sheer force of this invisible sea. And this ghost is powerful. We call its repulsive gravity, dark energy, the force that's accelerating the expansion of our universe and deciding its ultimate fate. The vacuum gives particles mass, allowing for atoms, stars, and us. The very structure of reality is built on this energetic nothing. So, we have to update our picture. The vacuum isn't an absence. It's a plenum, a substance teeming with potential and furious activity. Emptiness isn't empty. It is the ground state of everything. The ghost that haunts the vacuum is the very heartbeat of the universe, a constant reminder that even in the deepest silence, the song of existence plays on. The universe isn't built on a foundation of nothingness, but on a foundation of possibility. And it seems that in our cosmos, true nothingness is the one thing that is fundamentally impossible. If you're fascinated by the deep and weird nature of reality, you might enjoy our video on what existed before the Big Bang. To keep exploring the biggest questions in the universe with us, make sure to subscribe and hit the notification bell. Thanks for watching.